Hey, how are you? You
Hi, good morning. I'm good. How are you?
doing well, good to see you. So I believe we all got an email, right? That we should sign up for an email for access.
Yes, I can see a number of students have signed up for it. I did send over two files yesterday via email. Do you know if those were uploaded to the workshop website?
Yeah, so who here has not received the email about signing up for Nexus? Did everyone get it? Yep, okay. No, I think we're set. If anyone has any issues, let us know.
Can I ask if the two documents were uploaded to the workshop website, the two notebooks?
You like to, we can get to it now. Give me a second. You sent did you send an email about this?
Yes, I sent two notebooks yesterday.
Okay, we will get those, I guess. I see, all right, we'll get to it. What I can also do is I'm gonna email these out to all the
Y- y-
everyone who registered.
that might be easier and quicker. Thank you.
Yeah, absolutely. The Grover search, right, and the Guppy example?
Yes, there's two Guppy temp examples and Grover search. Yes.
Yeah, we'll send that out.
The only parts they use AI to turn bullet points into reports and contains. So doing that into bullet points.
All right. Give it a minute and send it.
Okay. I don't need it to start, so I'm happy to get started if we want to keep on time here.
Okay, all right, that sounds good. All right, well, good morning, everyone, and welcome back to day two. And just a few announcements. Remember, we have refreshments outside, bagels, there's light breakfast. So we're excited to pick up today with the Nexus demo and overview. We're joined with Mikhail Schick.
Yeah.
Who's joining us remotely. Mikhail, where are you coming from? Where are you
So
from?
I'm based in London.
London, okay, that's all London, all right, great, that's why they couldn't be here today. So we'll pick up with that, I just forwarded an email with the Python notebooks for today's session. So give it if it hasn't been received yet, you should have, did everyone get it? You see it? Yeah, all right, perfect, if someone didn't receive it, let me know. and I'll make sure to forward that. We're also gonna get it on the website, shortly. All right, I will turn it over to Mikhail, and we'll get started.
Thanks. Hi, everyone. I don't see anyone's faces, so I
I
apologize.
will
I'm looking at.
change that. in one
Okay.
second.
Okay. Yeah. If you can do that, it would be great. No, that's great. Thank you so much. Hi, everyone. My name is Mikhail. I'm based out of London, as I said earlier, and I am the product manager for Quantinuum's Nexus platform. Um, the session today is kind of a mixed bag of kind of describing what our Quantinuum's platform is, talking a little bit about Nexus, but the actual goal is to get you guys onto the platform itself and kind of run a couple of programs along with you. I was told though that there's a mix of people here who are familiar with quantum programming and who are not. So show of hands for people who've never written a quantum program before. Okay, and people who have written a little bit of quantum programming before, who are familiar with quantum programming. Okay, great. Okay, so that actually helps me because the way I've structured today's talk is it's an hour. I'm going to kind of spend the first maybe 10 minutes talking about the very basics of quantum computing. Now, I don't expect, I think we have a couple of quantum professors in the room. I don't expect to be able to do in about 10 minutes what they do in a semester's worth of teaching. I think what I'm going to do here is to talk about things that are exciting. A lot of you have never done this before, but you've heard these terms being thrown around, right? You've heard about superposition and entanglement and qubits, and it's all magic, right? So I'm going to try to demystify that magic in completely non-technical terms. I'm going to keep it very, very high level. So for the few people who do understand quantum mechanics and quantum computing in the room, I'm going to apologize. The first 10 minutes might be a little basic for you, but hopefully what that'll help is that for everyone to kind of understand what I'm talking about. Um, then I'll do a quick couple of slides, not a lot, talking about what Quantinuum a stack looks like. We have a full stack platform that goes all the way from a programming language, a platform, all the way down to actual quantum hardware. I'll describe that. And I'm going to try to make sure that all this doesn't take more than, say, 30 minutes to 35 minutes tops. What I really want to do today is to get you guys using Nexus. So all of you should have received an email from me yesterday giving you access to the Nexus platform, and you've just been given 2 Python notebooks. In those notebooks, there are a couple of examples that are very, very, very basic. So the most basic example is a Bell state, and there are more complicated examples like the Grover's algorithm, and there are very, very complicated examples like post-selection. So I'm going to take some time today to kind of walk everyone through the simpler examples, and we'll run them together. You have access, so you can run the notebook yourself. I'll show you how to do that. We will use Nexus for the whole thing. And then for all the advanced students in the room, the professor, you guys can kind of take away some of the more complex examples to do as homework. If you obviously have any problems with the homework, you can come back and reach out to me, and we can kind of help give you solutions to that as well. The goal of today is for you to leave the room with 2 things. Firstly, you are excited about quantum computing. It's cool. It's very, very cool. I didn't know about it before I joined this company. I think it's the future, personally. I think AI is important, but I think quantum computing is also equally important. And I'd like to get you excited about it as well. And B, I'd like you to get at least 10 minutes with actually using the platform itself. So you know how easy it is to use, and you kind of are onboarded. So, at the end of it, you should be able to use Nexus, and you should be able to write programs, and you should be able to get around the platform. How does that sound? Thumbs up for if it makes sense. Cool, thanks. I'm going to try to make this as interactive as I can. I think I don't have sharing requests. I can't share my screen. Sorry.
We'll change that in 1 second. Sorry, all the settings change overnight. Sorry about that.
It's fine. Okay, so I can share my screen. Thank you so much. Okay, so I have in total 17 slides, out of which, like I said, the first couple of them are definitely going to be very introductory. So let's kind of dive in. So I'm going to talk about our entire stack of products that is nexus. But before that, why worry about quantum? Why are we here, right? That's, I think, a kind of an important question. And the real benefit of quantum computing is that you can solve classically difficult problems, sometimes classically impossible programs efficiently. The one thing to think about is that quantum computing is not just faster computers. So you can't just take your existing programs that you write in C or in Python or in Rust and run them on a quantum computer and just make it faster. That's not how it works. What it does is you have to take an existing problem. In this case, the example I'm going to take is a database search, and you think about it differently because quantum computers allow you to do things that classical computers cannot do and do certain things more efficiently. So I can fairly confidently tell you that you will not be able to play Counter-Strike on a quantum computer in the near future. Unfortunately, as much as you like it, that's not happening. What you can do, though, is you can do things like database searches. You can do things like cryptography. You can do things like material synthesis. You can do things like drug discovery. You can do things like medical analysis a lot quicker, but you have to think of things differently. So let's take a very simple example of a database search. So the simple example here is you have 8 coins and you flip those coins, and I'm trying to find out which of those coins landed on a heads, right? So our very simple example here is you're looking to understand, you're looking to satisfy fx equals to 1. So how would you do this on a classic computer, right? You had 8, you had 8 independent coins. They don't affect each other. So the way you would do it is you check the first coin. Is it a 0 or a 1? Is it heads or tails? No. Then you go to the second one, yes or no. Third one, yes or no. Fourth, yes or no. So in the worst case, you have to do 8 checks if the 8th coin is a heads, right? So the complexity of this and the runtime is basically O of n. Grover's algorithm is a quadratic search speedup. And that's one of the examples I'll show you today. But the gist of it is you would take all your 8 coins or your 8 states and you would put them in something called superposition. And I'll explain that to you what superposition is on the next slide. And then you would run operations on all of them simultaneously. So the way to think about this is you've flipped your 8 coins and they've landed in some shape. One of them is a heads, you don't know which one. And you say that the heads coins suddenly get heavier or suddenly become a little bit more red. And how that happens, I'll again explain to you in more detail. And then you make that effect stronger. So initially, all of them are on a flat table. And then you say the one that's heads is heavier, so it sinks a little bit more. And then you say, no, make the one that's slightly heavier a lot heavier. And then it sinks a bit more. And basically, those are the 3 steps you do for Grover's algorithm. And again, this might sound very abstract to you, and I'll show this to you in code in the example. And you also have a notebook that allows you to kind of go through it. So what is quantum computing? This is very basic. Again, apologies to the guys who are experts in the room, but at a very high level, you're taking advantage of a couple of very unique things that happens with qubits. And I'll talk about what qubits are in a second. And the 2 major concepts to think about are superposition and entanglement. And I'm sure you've heard these terms before. You've heard the famous Schrodinger's equation. There's a cat in a box. Is a cat dead or alive? It can be both until you open the box. That's exactly what superposition is. Until you actually look at it, or in our world, until you make a measurement, a qubit can be both a 0 or a 1. So you use superposition and entanglement in order to encode information and then manipulate information to get the kind of algorithms that you want to do. So superposition, like I said, is you take these 2 classical bits, right, a 0 or a 1, and you encode them into a qubit so that it is all possible variations between a 0 and a 1 simultaneously. And you can do transformations on it. You can take actions on it. And it will not resolve to a 0 or a 1 until you make a measurement. Okay, so that's basically the idea of superposition. Now, qubits come of many types. The 2 major technologies that are out there are superconducting qubits, which is the big player in this is IBM, and then you have ion trap ion trap qubits, which is what Quantinuum is one of the leaders in. So I'm not really going to go into qubit physics right now, but all you need to know right now is you can put this qubit into a 0 or a 1, and it will remain unknown to you a 0 or 1 until you do a measurement. The second concept to think about is entanglement. So entanglement says you can bring two qubits together, and the simplest way you can see in the diagram on the bottom is you use a laser to entangle them, and then even if you move them apart, they will kind of work in tandem. And that's when you hear about all these cool things in media and in books and all that. If you turn one, the other one automatically turns. And technically, this could happen faster than light. So if you move them sufficiently far apart, they would move faster than light, and it breaks my brain. I'm not going to pretend I understand how it actually works. But these two concepts are really important to quantum computing. The other ones that I'll just briefly mention are the act of measurement. So as I mentioned earlier, it could be a 0 or a 1 until you measure, and then a qubit is forced to resolve into either a 0 or a 1. And then there's a concept of interference, which is each of these qubits would have their own wave function, and two qubits that are entangled, their wave functions could either attenuate or destroy each other. So you have destructive interference or constructive interference. But for my examples today, we don't have to worry too much about that. So how do you think of a circuit? How do you think of a program? So, if you think about the old transistor life that, you may have had in your first year of engineering or of computer science, or, whenever, you thought of things like these gates you see on your left, right? You have an AND gate, you have a NOT gate, you have an XOR gate, you have a NAND gate. You can think about quantum gates in a reasonably similar manner. In fact, at this state of quantum computing, only in the last maybe 1 or 2 years have we kind of moved from thinking at a very transistor level to actually thinking of programs. I think Guppy is one of those languages that was released last year, actually, that allows you to almost stop worrying about transistor level coding and thinking about programming. So on the left, you can see you've got your classic gates. On the right, you can see something called a circuit notation. So the best way to think about it is each of the horizontal lines are your qubits. So the line right on top is your Q0. Your line below that is a Q1, line below is a Q2. Each of them are qubits. And these qubits kind of evolve over time. So as you go from left to right, you have a time scale, and each of the actions that you perform that may be on a single qubit, they may be on multiple qubits, kind of happen on a time scale. So you can see on the right-hand side diagram, you see a line with a circle that's happened at one time. Then the yellow T and the purple T are happening simultaneously. Then you have the H with the other line. Then you have the T dagger, et cetera, et cetera. So it's kind of like an order. It's a sequence of operations. The one difference to keep in mind when you kind of make this analogy with classical circuits is that you will always have the same number inputs and outputs. Qubits cannot really be destroyed. They can be discarded, they can be measured, but at the end, the number of qubits you start with are always going to be the number of qubits you end with. You start with 3 qubits, you'll end with 3 qubits. Some of them may not be useful, but they will still exist. So as you can see, they always kind of continue to exist. A fun way for me personally, when I started learning about quantum computing, was I've always thought of these as guitar strings. The guitar strings always exist. Those are the lines. And then the operations are notes. So every time you press a string, you do a T note, it's doing something. It's shortening the length of the guitar string. So something similar here. They're very sequential operations that you will carry out, sometimes over multiple qubits, sometimes over a single qubit. But the good thing about quantum computing and the better thing about Guppy is you don't have to really worry about what's happening at these on the hardware level. You only need to worry about the operations. You only need to worry about these logical gates, and I'll talk about gates in a second. But you need to think about this very much only in a software world and not too much in a hardware world. So we've kind of described how a circuit notation looks. These operations that you would conduct on these qubits are considered, they're called gates, and each of these kind of transform these qubits in a slightly different manner. And there are obviously many gates. You can pretty much, technically, you can do almost anything to a qubit with a laser, but there are some standard gates that we tend to use. And on the left, you will see a list of some of very widely used gates. But for today's talk, and especially related to the example I'm going to show you, there are a couple of gates that are kind of important, and those are the ones listed on the right-hand side. So the most important one, I guess, is the H gate. It's called the Hadamard gate, and that kind of does the superposition I was telling you about earlier. So it transforms a qubit into this indefinite state of having both a 0 or a 1 with an equal combination of both. So if you were to take a qubit, do a Hadamard gate, and measure it, you will always get 50% of the times a 0, 50% of the times a 1. Okay, so it's a very even split. What that means, though, is that typically you need to run your program multiple times, and your result is going to be very probabilistic. You're never going to be able to say it is exactly a 0 or exactly a 1. You're going to be able to say it is statistically probable that your answers are 0 because you have 95% of the answers are 0 and 5% of the answers are 1, so you say it's 0. And again, the examples that I would show you live and we walk through it will kind of describe this a little bit more. So the H gate is one of the few gates that are not really very obvious in the analog world, but some of these other gates would be. So the Pauli X gate, it's like a NOT gate. So if it's a 0, it becomes a 1. If it's a 1, it becomes a 0. So in the classical world, it would basically be a NOT gate. A controlled NOT gate is a gate where, depending on your control, so you say it's qubit 0 and a qubit 1, depending on the state of qubit 0, it will do a NOT operation on qubit 1. So you're controlling one by the other. The second obvious version is a CC NOT gate. So you're saying, I'm going to take 2 qubits, and then depending on the state of both those qubits, I want to affect the third qubit. And then logically, there is a CCC NOT gate. So you have 3 qubits that are affecting a fourth qubit. So that's called a C3 NOT gate or a C NOT gate. And then you have a swap gate that says there's 2 gates, there's 2 qubits. Let's assume there was 0 or a 1. I want to swap them to make it a 1 or a 0. So again, I'm not going to try to be exhaustive. I'm not going to explain the physics. Again, this is a semester's worth. If I could explain all this, all the professors at JHU would not have a job. I don't want to take their jobs away. I like people to be teaching. So I will not pretend I can explain this. But hopefully this gives you a very general idea of what gates are. If you are interested, there are some really good books that explain these gates in detail. But for today, this should be enough. Okay, so now let's talk about some very
I got a quick question.
Yeah.
On the last slide, so these are physical operations in the sense that something on your computers is doing this transformation, right?
Yes.
Is that what's going on?
Yes. So that's exactly it. So I'm going to go back to my previous slide here really quickly. All our operations are kind of are executed using a laser. So it's very cool, but literally you have this a single ion of a ytterbium atom that's held in a trap, an ion trap. The ion is trapped, and then you shoot a laser at it. Okay, and the energy of the laser and the angle of the laser basically determines what happens to it. So if you shoot the laser with a certain energy, it's just enough energy to move the electrons of the ion in between what are called hyperfine states. And that's it's in between 2 actual states. If you think about your 101 chemistry, you have these different state energies. The laser basically puts it in between the 2. So it hasn't gone all the way up, it hasn't gone all the way down, and that's how you get superposition. So yeah, we actually physically manipulate the ions.
And so the fact that you have these things in a box that you can't see and you don't know what state they're in, a NOT gate, even though you don't know what it is, no matter what, is always going to flip it.
Yes.
Okay.
Yeah. Yeah. The interesting thing, though, is basically the next slide. The NOT gate will flip something from a 0 to a 1. But what happens if the qubit itself is both a 0 and a 1? Right. What if it's in superposition? Then what happens? So that is basically the example I'm going to walk through today. It is very, very cool. It's called the Bell state. So it's the diagram on the top. So you have two qubits, Q0 and Q1, and you have two classical bits, C0 and C1. And all we're using the classical bits for are to store your measurement. Okay. So again, going from left to right, on Q0, what I've done is I've taken this qubit, I fired a laser at it, I put it into superposition. So it could be a 0 or a 1. I don't know. Okay. And now I'm going to do this controlled NOT. So controlled NOT here means depending on what Q0 is, I want to flip Q1. Now Q0 could be a 0, in which case you're not flipping the Q1, or it could be a 1, in which case you are flipping Q1. So you expect 50% of the because Q0 could be either 0 or a 1, which is 50-50. Q1 is also forced to be 50-50 as well. Does that make sense?
Because they're entangled, you're saying?
Because they're entangled, yeah. So I should have mentioned this. So when you have the vertical line, that means these two, you're doing what's called a 2-qubit operation as opposed to a single qubit operation. And the 2-qubit operations are now entangled. So you've done your superposition, you've done your entanglement, and then you're just measuring it. Now, because Q0, if it's a 0, it forces the second qubit to become a 0. If it was a 1, it forces the second one to become a 1. So what we're going to see when we run this code is it could be four options, right? It could be 0, 0, 0, 1, 1, 0, 1, 1. But when you run this program, you're only going to get 50% 0, 0, 50% 1, 1. Now
yeah, go ahead.
I'm curious about like how Helios is working, just because you only have 8 ions in the trap at a time, right? And then you move them around. So if you want to use all 98 qubits, how do you control all 98, and are all 98 entangled?
Yeah, so that's what I was saying earlier about entanglement, right? Is once you bring these two together, you can move them apart and they stay entangled. You don't have to physically connect them anymore. And our Helios architecture says that because we've got a ring and these gate zones, you can actually, and one of the beauties of ion traps is that you can actually physically move the ion. So what we basically do is, if you want to connect qubit 1 with qubit 94, we bring them together, do your operation, and then move them apart, and they will stay entangled.
Cool.
Does that make sense?
Yeah.
So this is really this really has no analog, right? Because if I'm thinking about bits in the real sense, I mean a bit on a computer, if it's 0, this is not going to affect a bit next to it, a 1, unless I make it that way, right? In this case, you're saying they are intrinsically tied, and so we have some sort of, you really have like extra options here in this landscape, if you will.
Yeah, but it's a choice. You don't have to entangle them. So as you can see in the diagram, I've done a 1-qubit operation on Q0. I didn't need any other qubits. I've then tried to entangle them, and now they're entangled.
I see.
So you can do individual operations. You can do 2-qubit operations. You can do 3-qubit operations. And the ability for us to move the ions around physically means any qubit can touch any qubit. So that's what we call all-to-all connectivity, which is one of the big differences, one of the leading differences actually between the ion trap technology and the very adjacent neutral atom technology to the superconducting technology, which is very different. In superconducting, you can't move anything around. And in the superconducting world, you have to think about things like swapping, whereas we don't have to worry about swap gates.
I see. So your ability, and I guess what you're saying here is that the ability to entangle gives you more options for the logic. I can do more elegant operations, which translates to more interesting logic, perhaps with lower power or even faster, right? Is that what you're saying?
It's more, I would, the word we would like to use is efficient, because you can't, as I mentioned to start with, this is not just a faster computer. It is a different computer. You cannot think about this in the terms of just running a basic transistor logic or just writing Python programs. You have to rethink how you do your operations. So there's a little bit, I will say there's a little bit of a learning curve, and you have to kind of break away from classic Python thinking or classic programming thinking into quantum thinking.
We got more questions here. I hope it's okay. Go ahead.
Yeah, for sure.
pretty basic question. Do you assume that both qubits initially are, well, how are they initialized? Are they always initialized to 0 or to
So
1? Or how do you
it
start?
so that depends on the kind of program you write.
Uh-huh.
So they
What
could be
makes
initialized to
the
0.
description here, because I'm trying, I get, if I play this through my head, I get the opposite result. So I'm thinking maybe it's because I'm assuming something about the initialization.
Yeah, I mean, you could initialize them to you don't initialize them to any value, right? They're basically they're just ions to begin with. They're not 0 or a 1. They're just there.
Okay.
They exist.
But
And
what
then
about the description here? What are you assuming?
in the description here, I'm assuming that it's both. You're basically uninitialized, and then Q0 basically you're putting into both a 0 and a 1. So Q0 starts off as nothing. Let's assume it's nothing, and then you're making it both a 0 and a 1, and therefore Q1 is nothing, but it is affected by Q0. So if it's a 0, Q1 becomes a 0. If it ends up being a 1, Q1 becomes a 1.
Because I thought X is a flip. So in my mind, if both started at 0, for example,
So
then I would get X. I mean, you get the entanglement, but then basically, if Q0 is 1, then Q1 will be 0, etc. Like, which
no,
is the opposite of what you wrote.
yeah, you'll only get a 0, 0 and a 1, 1.
And I guess the point, I mean, you're saying here Q0 is in a superposition of 0, 1, right? So they're both in sort of superposition always anyway.
No, so Q1 doesn't start in superposition.
All right, okay.
Wait, did I write this wrong? Hold on, this text is in the way.
Interesting.
Yeah, no, that's correct.
Okay. And so if you don't initialize it, then you don't know what you don't start with. But you're
Yeah.
still doing math that works, I guess, at the end.
Yeah, so all your math basically happens, you're doing all your transformations. Your math only happens when you actually measure it.
Okay.
Hello, sorry, can you hear me? I'm coming
Yeah.
from online.
Yeah.
So just to clarify, the X gate sounds like what you're saying, which is not the classical way of thinking about it. The C naught gate here flips the state of Q0 and imposes it on 1. It doesn't flip the state of Q1.
Yeah,
Because
sorry.
Q1
So
didn't have a state to begin with. Is that
yeah,
correct?
so no, I should be clear. So the NOT gate, not the control NOT gate, flips it. The C NOT gate only flips it if it's a 1. So
Right, when you say it flips it, what does it flip? Because when you said Q1 itself is not initialized, what is the meaning of flipping something that is not initialized?
if it's not initialized, it's setting it then. You're forcing it to be a 1.
Mikhail, do you mind if I just quickly jump in?
Yeah.
Yeah. So here the actual action that the C naught gate applies is on Q1, right? And it's dependent on Q0. That's why that little black dot sits on the Q0 line. I think there has been maybe a bit of confusion. So in this case, as far as I'm aware, the states of qubit 0 and qubit 1 are initialized in the 0 state. Whenever we write a circuit like this, we're assuming that we're starting in the all 0 state. Now, physically, that doesn't necessarily happen, and there are actually a few different reasons why you might want to have a quote-unquote dirty state. But in this case, yes, we start with 0, 0 and go through the circuit. Does that clarify your question?
Yeah. Yes, except that if X is a flip, then if Q0, if Q0 is 0, then Q1 is 1, right?
Yes, yeah, exactly.
So the point on the slide isn't correct.
No, so it's a controlled NOT. So it'll only flip if it's a 1. So both initialize at 0. If Q0 is a 0, it doesn't do anything to Q1.
Oh, I see. Got it. Okay.
So it's a controlled NOT. So I'm saying the difference is it's not a true NOT.
I see. Okay. Okay, that makes sense. Thank you.
One more
Okay.
question, because you mentioned it, but I don't know, so some of this logic, because you said that this is all done by laser. This translates differently on a superconducting qubit, but you're saying that they still have the same capabilities, or are you saying that there's
Yes.
some capabilities that are different between the technologies?
There are some capabilities that are different within the technologies, but the gates are more or less the same. The way they operate are the same.
Okay.
There are some unique gates, but in general, the ones that I'm talking about, the basic ones are very similar. Okay. Any other questions before we kind of run through to an actual demo? I'm going to speed up a little bit.
One more question.
Maybe just a quick question, like maybe naive, but why the property is 50%, 50%? Is it like the energy of the laser can kind of determine whether the 50% can change above or below that?
Yes.
I'm not sure I understood the question.
But both Q0 and Q1.
I mean, for example, if you're using the laser to kind of say the superposition can kind of sit in between the 0 and 1, so is it always 50% result to be 0 and 50% to be 1, or is there some of the kind of the change based on the laser energy?
Yeah, so the concept of putting a gate into superposition, so this particular laser will make it 50-50. There are other laser operations that would put it, some of the other gates would put it in at a different energy level. So that's how you would manipulate it to a non-50-50 state.
Oh.
So then it's not just exactly 50-50 or nothing. There are other gates as well.
Thank you.
Okay. In interest of time, I'm going to kind of run ahead because I really want to spend some time doing these programs live. So let's talk about our Quantinuum platform. So as I mentioned, historically, we've always really spoken about, we've only so far spoken about these programs in terms of transistors and in terms of circuits, but we are kind of now getting to the point where developers like yourselves can start thinking about code, and Guppy is really one of those tools that allows you to do that. So within Quantinuum, we have a couple of different layers. We have these applications on top. So we have in Quanto, which Kieran is going to talk about right after this presentation. It's focused very much on quantum chemistry, but it's an application. Then you have Guppy, which is the language to program, and I'll talk about that a little bit. You have these tools. You have Nexus, which is a cloud-based platform, and then you have your actual quantum hardware. So essentially, the higher up you go in the stack, the more abstract you are, and the less you have to think about the actual lasers and the actual transports and the gating operations. The example that I'll show you in the code, you really don't have to worry about what's happening. You say, do an H gate, it'll do an H gate for you. Do a C naught gate, it'll do a C naught gate. And you don't have to worry about anything below that. So it really works well with this audience because as long as you're a good programmer, as long as you understand the semantics of Guppy, you can start programming a quantum computer. So we've got three basic things within our stack. You have Guppy, which is a quantum first programming language. You have Nexus, which is the cloud platform. Its basic job is to take your program, transform it, compile it, and then send it to a backend or a machine. The backend could either be an actual quantum computer or it could be an emulator. And in our example, we're going to use an emulator. And the emulator that we're going to use is based on Selene. Selene is our framework for emulation that's hosted within Nexus. Selene is also an open source platform. So if you want to download it to your computer, and all these programs, by the way, are open source. So Guppy is open source, and Selene's open source as well. So you can install it locally. You can run it. You need Nexus in order to submit to Quantinuum's hardware. So Nexus is a cloud platform. Now we're kind of getting into stuff that's a little more for the advanced users. So the different types of programs that Nexus can accept is Guppy, which is our new programming language. It can accept QIR, the quantum intermediate representation, which is a industry standard, and it can accept PyTicket, which is our legacy language. It gives you access to a number of different types of machines. You have the actual Helios machine that you've probably heard about. That's the quantum hardware. There are a number of GPU-based emulators and cloud-based emulators that I will show you. And then you have Selene. And then there are a number of different tools and capabilities like qubit reuse, leakage detection, and quantum error correction toolkits that are within Nexus. And all this information that you write, all the programs, all your results are all stored within Nexus, and you can see the probability distribution on the right-hand side at the bottom. So basically the way it works is you write your program in Guppy, you submit it to Nexus, and the Nexus will then push the job to Helios, which is our latest generation, H2, which is our last generation, and Selene. But you can also use QIR, which is an industry standard, to submit through to Nexus. So Guppy, our big programming language, super easy to get started with. You just pip install it. It is an open source product. You can go to guppylang.org, and that's where you'll find all the documentation you're looking for. You can find there are links to the GitHub repository. If you are interested in contributing, you can do that there as well. Basically, it is very much a Python-like language. So if you're familiar with Python, it's in fact embedded in Python, and it basically looks like Python, and you basically use the Guppy decorator. So on the right-hand side, if you remember the Bell State example that we spoke about, on the right-hand side, you can actually see the code that we will run. So you put the decorator at Guppy, you define a function saying Bell State, you initialize your 2 qubits, so you're saying qubit Q0 and Q1 are your 2 qubits. You say H, which is a Hadamard gate, so you do Hadamard gate on Q0. You do a CX, which is a C0 gate on both of them, and you return them. So that's your function. You would call it within main, and then you would output your results to your 2 classical qubits. You would then compile it, and then you would then submit your job to Selene, which is our emulator, and that allows you to actually run it. The emulator does come with a number of different options, and I'll talk about that in a little bit, but that's the general workflow. You write your program, you compile it, you send it for execution. Why is Guppy cool, and why do we think it's going to be useful to programmers? Is because it's embedded in Python. So you can use NumPy, you can use Matplotlib, you can use pretty much any of your existing workflows. If you know how to program in Python syntax, you pretty much can get started with Guppy straight away. And it has a number of safety features so that you can't do things that like type safety that kind of make sure your programs will not have certain errors. So and now getting a little bit more into detail about Guppy. Again, this is for I think a little bit more of the advanced users. Guppy is one of the few languages that has control flow. So when I showed you the circuit representation earlier, I said all the things are sequential. So if you're trying to do something like a loop, for I equals to 1 and 10, you would actually have to unroll your loops and write the same gates 10 times. Guppy allows you to actually write things like loops, do things like branching logic, and control the flow of your program. You can use you can use a lot of classical compute, so you can do a lot of classical operations alongside your quantum operations. As I mentioned, it is quite strongly typed, so it helps you avoid certain quantum specific errors. You can use all your standard data structures, both in the classical and quantum context. Qubit safety, as I mentioned, there are certain risks like no cloning, and there are things like memory leaks that, again, a little more advanced, but these are things that Guppy just enforces for you, so you don't have to worry about. And as I showed you in the Bell State example, you have these first-class functions. You can use qubits and kind of pass them between functions, and just like any other value, like an integer, and it'll take care of it for you. I'm actually going to, in the interest of time, I'm going to stop the slides here and kind of jump to how many slides did I have left? I had a couple of slides. I'm going to jump to the platform itself. I've given you all access to Nexus. So if you want to follow along, you can follow along with me. I'm going to basically log into my account of Nexus. So you all should have had access to this. So when you log in for the first time, you'll see something like this. It's going to Jupyter Hub, actually. Let me go to So the home page will look something like this. You have all the jobs you run in the middle. On the right-hand side, you've got your documentation. On your left side, you've got something called quotas, which again, students don't need to worry about. These are mostly for admins. What I'd like you to do right now is basically start an environment. So you're going to go to lab. I'm going to launch a new notebook. And this should be familiar with anyone who is familiar with using Jupyter Hub or any other environment. It basically is hosted in the cloud. The benefit of using the cloud version is all the dependencies, all the packages, all the authentication is already taken care of for you. So it kind of allows you to just get up and running. If you want to use it locally, if you prefer using VS Code or something like that, you can do that as well. The interface is pretty simple. So I'm going to basically just drag and drop the programs that I sent you. So the first one I would recommend you start off with is the Guppy examples and homework. So I'm going to drag and drop that here. It's uploaded it. On the left-hand side, there are a large number of example notebooks. So these example notebooks here will help you get started if you're interested. But I'm going to kind of focus on the examples I sent you right now. So I've clicked on it, and I'm going to basically show you the Bell state circuit that we spoke about. Okay, so has anyone had any questions or problems getting to this point?
So you created a new project, is that what you did?
I just uploaded the notebook that I sent you, and I double-clicked on it, and it opened the notebook.
Okay.
And basically, at this point, you're ready to start running a quantum program. So for people who are inclined to look at the math, this notebook does contain some of the math. I'm going to skip over that in the interest of time and to kind of let you guys do the circuit itself. So it's basically this first example is exactly the same code I showed you in the slides. So I'm going to basically initialize 2 qubits, put a Hadamard gate on it, put a CNOT gate on it, and return these gates. So I'm going to run this first cell. As you can see, it is checked. It's going to check for you. So Guppy has this automated checking. Now, as I mentioned, one thing to keep in mind about quantum programming in general is that all these results are going to be probabilistic. So unlike a regular program where you would just run it once and you would deterministically get either a 0 or a 1, quantum programs are probabilistic. So you want to run the program many, many times. Each time you run the program, in the quantum world, we call it a shot. And the more shots, the better in general. For ion trap hardware, you tend to need fewer shots than superconducting hardware. We typically say 1,000 shots is usually a good number. For superconducting, you would normally do like 10,000 shots. For us, 1,000 shots is enough. So I'm going to run this program. I'm saying I want to run 1,000 shots, and I'm going to basically use the inbuilt emulator, and I'm going to put a seed of 1 just so that I know exactly what the results will be. So I'm going to run that, and then I'm going to basically print out the results. So as you can see, the results are 0, 0 is out of the 1,000 shots, 515 results were 0, 0. 485 results were 1, 1. Why is it not perfectly 0, 0? It's because machines have error. So in the difference between, if you were to try to simulate this, when you would get exactly 0, 0 and 1, 1, but quantum machines basically have slight errors that creep in, and our emulators basically try to model that error. So the emulators will attempt to produce some of that noise, and that's why it's not a perfect 0, 0. And basically, you're going to get a result. You're not going to get the other two 1, 0 and 0, 1 states. You should have gotten a 0, 0 and a 1, 1. So that's a very simple Bell state. Now, what if I wanted to do something a little more complicated? I want to do the same thing, but over multiple different qubits. So in this case, remember that the qubit 1 is forcing the result of qubit 0 is forcing the result of qubit 1. Qubit 1 is forcing the result of qubit 2. Qubit 2 is forcing the result of qubit 3. So what would you expect the outcome to be here? Anyone like to guess?
It started with 1, you said?
It could start with either a 0 or a 1. But then after that, every other result is forced.
Well,
Is it all zeros or all ones?
That's exactly correct. You will get 0, 0, 0, 0 or 1, 1, 1, 1, and none of the other states. So let's try to run this. Does that make sense to everyone?
Yeah.
By the way, you can run these notebooks on your own. I'm kind of running this through a little quicker. The reason I wanted to share these notebooks with you was you can run this on your own as well. So I'm running the program. I think I'm at this point right now. Oh, I injected this in the wrong spot. Oh, I should have copied this again. So it's running and something's going wrong, but essentially you will get a 0, 0, 0 and 1, 1, 1. I'm not going to run some of these other more advanced examples in this talk because they are meant for some of the more advanced students. Does anyone have any questions about these first two programs?
I guess I just wondered, how's the emulator simulating the noise? You mentioned.
Yeah, so we have a proprietary noise model that is based on the actual hardware that we have. So it takes the actual characteristics of noise that we expect on the real machine, and we use a proprietary noise model to bring it into the emulator.
Okay.
And so the emulator is just running on a CPU node somewhere on your.
So we have a bunch of different. So maybe that's a good thing to talk about. So we have a bunch of different backends, but we have basically 3 families of products. We have the actual quantum computers. Then you have GPU-based emulators. So these are running on actual GPUs that are based out of Colorado. And they're also running, we have cloud-based emulators that are running solely within Nexus. So right now, the access that you have through your trial would be for the cloud-based emulators, but they have the noise model as well.
Got it.
Any
I
other
just have a
questions?
question about emulation. So when you say you're doing emulation instead of running an actual quantum computer, is this you're just sampling from distribution with a random number generator in the background?
No, it's actually I mean, if Kieran, maybe you want to answer this one. I'm going to be a little fuzzy on this.
Yeah, sure. So what we have for an emulator basically is you build up a representation of your system as a matrix, right? So at the start, you would have the all 0 state, and you build up some matrix, and then you can go through applying the gates or the matrix representations of each of these gates. And then you get to the end of it, and you have some representation of basically the whole circuit in a matrix form. And at the end, like solving that for some specific vector gives you your output, right? Gives you exactly what you measure at the end. And I would add that the noise models, how they actually physically add the error is by randomly, well, not quite randomly, it depends on the noise model that Makar was talking about, but it injects sort of random gates, we call random Pauli errors. So it injects random NOT gates at certain points, so that would totally flip, right, the specific bit that you're looking at. Or one bit in a large superposition, and that would of course end in some error. Does that make sense?
Yeah, thank you.
Okay.
So your emulators run on any computer, or because it's proprietary, you can only run on your system?
So the Selene emulator is open source. You can run it anywhere you want. If you go to our documentation site, you can download it and run it yourself. The noise model is proprietary, and that we can only run on our on Nexus.
But presumably you need the noise emulator to run Selene, right?
No, you can run it with a generic noise model. You can build your own noise model, or you can run it perfectly clean without the noise.
Got it.
So, I have a question about your noise model you're choosing. So, are you I can do this for Karen. So you mentioned it's a stochastic polyerror model. So you're not actually modeling it as CBTP maps applied to like to some set of unitaries. You're actually just sort of almost like sampling like you would like you're doing like a Clifford circuit. Just in this case, it's not Clifford.
Yeah, exactly. Yeah.
Okay, all right.
Okay, let's maybe try to move over to the next one, which is Grover's search. So I'm going to import that as well. And again, I'm going to double click on that. So I'm opening it. Now, this could be a fun exercise for all of us to do. If you kind of scroll down the code, what the code is trying to do is find a certain combination of qubits. So let me see if I can find it in this. Okay, so basically, if you go down to the second cell, there's something called the marked state. So marked state here is the ideal answer you're looking for that the program doesn't know. So what I would recommend, just to make things fun, is change these numbers to 0 and 1 combinations that you like. So right now, my program is looking for a marked state of 1, 1, 1. And that's what it's going to try to find. But you guys can try something different. So you can make it 1, 0, 0, or a 1, 0, 1, or a 0, 1, 0, whatever. I'm going to change this to a 1, 0, 1. Okay? And then I'm going to run the entire thing. So each of you is going to get a slightly different answer. And that kind of shows that the algorithm does work. So I've made the change I'm looking for, and I'm going to hit run the entire code rather than run each of the cells separately. So you can see the first the first cell is running, and it's going to do a couple of things. But while it's doing this, I will also like to kind of show you something else while the program is running, is to show you the different types of backends we have within Nexus. So within Nexus, we have a bunch of different types of simulators and emulators. And you can see them when you hit the backends tab on top of the page. We have the actual machines. So you have H11, that's our old machine. It's a physical quantum computer. You have H11 lossless emulator, that is our an emulator without noise. You have the H1 emulator that has noise. You have the H2 computers. You have the H21E emulators, and then you have the H2 cloud-based emulators. So as I said, there are 3 varieties. You have the QPU, you have the GPU-based emulator, and then you have the cloud-based emulator. And these are all, so we have, as you can see, a whole number of different backends. And once you start playing around with the platform, you'll be able to see it. Hopefully the program has run now. Obviously not, it does something wrong. That is just how these things work.
Yeah.
Okay, I know what the problem is. I had this problem last time too. I'm going to change this name to gtest2 and then run this again. Any questions while we wait?
So in theory, we could make a emulator host on in our cluster here, right?
Yes.
Is the lossless emulator backend the same thing that we would get by just installing Guppy and Selene on a local machine?
You'd get a better version of it, actually. The one that we have in Nexus is using our older emulators. Selene is our new one, and we are in the process of kind of deprecating the old ones and keeping just Selene. Guppy is most efficient at Selene. And if you're interested in either using Nexus or using Selene locally, I would recommend using that one over the LE, the lossless ones.
Okay, and everything is just Python packages, or is there something other than the Python pip installs that I'd need to run this locally?
I believe they're all pip installs. But I mean, if you go to the documentation page, it'll give you all the details.
Yeah, Guppy and Selene are both pip installs. They're both Python packages. One thing I would mention is Guppy doesn't compile to, well, Guppy compiles to its own unique compiled form known as Hugger, and that's actually what's run on the Selene simulator. But that's not necessarily something that you actually need to interface with. If you're really into compilation, so specifically trying to make whatever program you have as efficient as possible in terms of running it on some emulator or hardware, then you might want to look into Hugger and how to start messing around with it. Yeah.
Okay, so the program has now completed, and as you can see, I changed the 111 to a 101, and over 1,000 shots, the result was overwhelmingly the result I was looking for. And you can obviously play with this on your own as well. But this is quite timely. We are 1 minute. I can say that I finished exactly on time, 1 minute before the end of the hours I was allocated. Any final questions? Any parting thoughts or comments?
I think we have a question over here.
Yeah.
So I had a very basic question. I should have asked this earlier. So in the beginning, you showed that like currently you are mostly talking about 0 and 1, but at the beginning you showed that block sphere. There I can see negative I, plus state, minus state. So qubits can also take those states as well.
Yes. So the qubits do and have a variety of like irrational states, but ultimately you're measuring into a classical bit, so it'll only be a 0 and a 1.
So those states nothing to do with our calculations, or
they are relevant. They do matter when you're trying to develop your algorithm. So yes, they and some of the other gates would put, like some of the phase flip gates would put, you would maybe need to use those to put the qubit into one of those into one of the states on the block sphere.
okay.
So you can think of it as when you prepare one of these states that's a non-classical state, it changes the distribution, right? So if you have relative phases, you create like these plus y states and so on. You'll get relative phases, but you have to change, sort of like to change your basis of measurement to take those values. But you can do it. But still, in the end, as it's, you can get the classical distribution.
Very cool. Thank you very much, Mikhail. This was great.
Thank you. Thanks for listening to me. I hope we were able to clarify the Bell state. I completely blanked on the fact that you always initialize to a 0, sometimes dirty. But I will say that all the participants of this workshop do have access to Nexus, courtesy of JHU. So you should definitely thank your professors in the room here. You feel free to play around with it. It's very hard to break Nexus. So, if you do break it, please let us know. But if you can basically play around with it, it's a very sandboxed environment. And all the example notebooks you can see on the right, if you go to the example notebooks, there are a couple of ones that are much more complicated, like a VQE example. So I would recommend some of the advanced students maybe look at that. In the Guppy examples notebook, if you scroll further down, there are a couple of more examples that are more, I guess, difficult and more advanced if you're interested in looking at those. But play around with those. We encourage you to learn, and hopefully you're excited about quantum computing in general. And with that, I will hand over to Karen. Thank you.
Thank you.
Great. You happy with me just jumping straight in? Can you guys see me?
Yeah.
Awesome. Great. So thanks, Mikhail. That was a great walkthrough of Nexus and Guppy and Selene. So first of all, before I jump into my presentation, my demo for today, I'd just like to sort of make a little bit of a connection between what Mikhail was saying and my talk yesterday, because hopefully most of you were here for my demo yesterday. We talked about, or Mikhail brought up this idea of entanglement, and this being quite a unique property that we can take advantage of with quantum computing. And I was talking yesterday a lot about electron correlation, right? This interaction between electrons. And these two sort of ideas are intrinsically linked, right? In quantum computing, we're able to create states that are quite highly entangled, right? States where the qubits are interacting with each other in quite a close manner, and actions on one qubit affect actions on another. And this is the same for electron correlation. The interaction of one electron with another is affected by all the other electrons around it. So I just wanted to make that sort of connection there to make you think maybe, oh, okay, in physical systems and chemical systems or materials, if we want to capture this quantum mechanical nature, then maybe it's a good idea to start using a quantum mechanical computer, because we can actually represent our system in a bit more of an accurate way. So without further ado, I'm going to jump back to my notebook here. Now, I realized that yesterday I had my notebook still in dark mode. This is now in a lighter mode. Is this easier to see or harder for people in the room? Any consensus? Easier? Sorry, I didn't quite hear you.
Easier.
Easier. Great, great. I apologize about yesterday. I hope that it wasn't completely impossible to see. Okay. So like yesterday, please interrupt me. I'll try and pause at a few points. But today we're going to do a very quick overview of what I talked about yesterday, and then jump into how we might use Enquanto with Nexus, and show you some of the more advanced things that you can do with Enquanto that are more closer to the idea of quantum computing in that, well, specifically looking at compilation. So we've had an introduction from Mikhail into what gates are and what a circuit looks like. So we're going to introduce compilation and why that's important, and then start thinking about noise. And we're going to run some stuff on our emulators. So Mikhail also mentioned the emulators, and I will sort of refresh you on that again when we get to it. But again, please just shout out if you've got any questions. Okay. So again, really quick overview of yesterday. I introduced Enquanto, and Enquanto is this modular Python package for doing quantum computational chemistry. It has all of these different parts that allow us to do some classical computational chemistry first, and then map the problem into the quantum world. Start deciding how, or what and how we're actually interested in measuring, and then interacting with different backends like Nexus we're going to see today, and then how algorithms can be used in totally different ways. Now, today we're going to focus a lot on protocols, because protocols are where these circuits that Mikhail introduced are really built within Enquanto. So that's where we're going to sort of focus on. And we'll start very quickly, basically stealing a little bit from yesterday. If you remember, we walked through, well, we used the Express module to bring in a representation of helium hydride. So this is what I've got here. I'm just pulling out, like I did yesterday, the Hamiltonian space and state of this helium hydride molecule. And again, building an ansatz. So this is, again, a representation of our initial state. And if you remember back to yesterday as well, we did a very quick VQE calculation. And I mentioned that VQE is a way of taking a parameterized ansatz and determining exactly what the ground state looks like. And one of the things that we can pull out of that parameterized ansatz at the end, once we've run our VQE algorithm, are the parameters that specifically specify that example or possible ground state. So I've just pulled the parameters from yesterday's notebook. And you'll notice again, we're just looking at expectation values, so just calculating ground state energies of the system. The first thing we're going to do, and I haven't actually been executing these cells, so I'll just go through, execute them. First thing we're going to do is start thinking about circuits. So at this point, we have a representation of our wave function, the trial system that we're looking at, and it's Hamiltonian, right? Which, if you remember back to yesterday, we have the Schrodinger equation. That's basically all we need to start trying to solve, find a solution, find an energy. And so we can actually represent this as a circuit, or at least our wave function as a circuit. And here we have some resource values. So whenever we're thinking about submitting to a quantum computer, we might think about our algorithms. We might think about how we're going to represent our system. We might think about how we're going to map our problem to the qubit space. But ultimately, at some point, we're going to have to look at the resources that our whole workflow is going to require, that is going to run on a quantum computer. And so here we've just got some values. So the depth is the number of, I guess, columns in those circuits, right? So you noticed how we might have a couple of gates applying to multiple qubits at the same time. As Mikhail pointed out, time goes to the right. So we might have, well, actually, it's probably easy for me to demonstrate here. So I'm printing the circuit here. So we have this single time step, if you can see my mouse, hopefully. This is one time step, another time step, another time step, and we go down the circuit. And so this circuit has a depth of 46. I think someone's chucked a message. Depth, yeah. Largest number of gates applied to a single qubit. Yes, I guess technically that's right. Yeah, that's a good way of thinking about it. Yeah. The largest number of gates applied to a single qubit. We can see the number of qubits, the number of gates in total, but quite often
depth refers to how many operations you can apply to a single qubit, before it fails, I guess you can think of it that way?
No. This is just sort of classifying the circuit, right? So the maximum number of gates applied to a single qubit for the circuit is 46. But overall, we have 4 qubits, and we have, variable amounts of gates applied to different qubits, sorry. So overall, the number of gates we have is 99. But depth starts to give us an idea of how, I was talking yesterday about QPE having long circuits, starts to give us an idea about how long our circuit's going to run for. And that's quite important because our qubits have what we call decoherence times. We talk about these entangled states, putting qubits into entangled states. Well, it turns out that, of course, you have an ion that's your qubit. This is quite a small particle, right? So there's lots of, as much as we can try and put it in a vacuum and try and keep it away from the rest of the universe, there's lots of just energy running around that might hit the ion and take it out of that entanglement state, or take it out of that superposition and put it into some other state within its hyperfine structure. And that's totally ruined, of course, the state that we've carefully prepared. So we want to apply our gates and apply our circuit as fast as possible in order to reduce the chance that this overall circuit decoheres, right? And so depth is quite important. Specifically, we start to look at 2-qubit gate depth, because it turns out that 2-qubit gates, well, maybe you can quite naively assume that 2-qubit gates are a bit more expensive. They're a bit harder to apply, right? Because we have to actually bring 2 qubits together and shoot the laser at both of them at the same point. So in terms of resources, it's important to have a look at how many 2-qubit gates we have and what the depth of our circuit is. And this is sort of the type of analytical thinking that we get to start thinking about when we're writing quantum programs. and submitting experiments.
So
Does
this,
anybody
on
have
average,
any
you're
questions?
saying, on average in this circuit that you have here, the longest number of blocks you have here is roughly 46, right? And one
Yeah.
line. And so how, with given the given state of the art, how long can you go before you should worry about decoherence?
That's a good question. I personally don't know off the top of my head. We would usually look at the 2-qubit gate depth. And it would be, I think, somewhere in the thousands for our latest hardware. And this is in part because we've developed a few techniques at the hardware level in order to reduce the chance of this decoherence happening. So this is a problem, obviously, you can start thinking about at the circuit level, trying to reduce the depth of your circuits. But we can also think about it at a hardware level, about ways to reduce this possibility of decoherence. So yeah, we think about depth, or specifically 2-qubit gate depth, in sort of the thousands, getting to the point where we're really struggling to deal with the decoherence within the system. Does that answer your question?
Yeah, that's great. Thank you.
Yeah. So, I mean, this circuit might have a 2-qubit gate depth of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, somewhere in the 10s, 11, 12, something like this. Yeah. So this is a relatively small circuit, right? But we're not quite finished because this is just the ansatz. This is just the representation of our state. What we need to do is we need to add it together with our operator in order to create an overall circuit that's going to allow us to measure the energy. Now, this requires a protocol, and before we get into building the protocol, we need to establish a connection with Nexus, because eventually I'm going to run these circuits on Nexus. So I'm just going to, in this cell, quickly define a few properties that are important for Nexus. So the first thing is a project. Within Nexus, there are different sort of levels, there is a hierarchy, I guess, of information. And a project is sort of a way to tag a set of jobs related to exactly that, a project that you might be working on. So I've defined a project called Enquanto Demos that I want to send all of the jobs in this notebook to. And then probably the most important thing is to decide what backend you're going to send that calculation to. So this requires defining the Quantinuum config. And here I'm going to choose the H2 emulator. So this, Mikhail mentioned these different types of emulators that we have. This is one of these cloud-hosted emulators on Nexus. And this is actually, I think, one of the emulators that you as users have access to. Yeah, this is the emulator that you might end up using. Selene is different, right? I mentioned yesterday that currently Enquanto is based on Ticket, and so well, there are ways that you can submit to Selene by converting the Ticket circuit into a Guppy program. But at the moment, the smooth transition from building a circuit in Enquanto and submitting it to some backend is via these backends here. So we've got H2 emulator, an emulator of H2, the previous generation of hardware. So I'm just going to instantiate that backend, and then we get to the protocol. So the protocol here that we're going to use is one that is quite often used when we want to measure some specific expectation value or some specific operator on a circuit, and it's known as Pauli averaging. So just a little bit about Pauli averaging. What we have here are a set of gates, right? We've mentioned. Not all of these gates are under the family of the Pauli gates, but one of them that is the X gate. I don't know if there are any others in here specifically. No. But we have the Y gate, the Z gate, and the identity. These are all Pauli gates. What Pauli averaging does is it takes the set of Pauli gates that represent your system and your operator, and it breaks them down into, in this case, commuting sets. So the Pauli matrices obey some commutation relations, and we can break these down into commuting sets that can be simultaneously measured. And so in this way, we can create multiple circuits that we will run in order to measure our specific expectation value. And so within Enquanto, building up a protocol requires first instantiating it. So this is what I'm doing here with this template protocol here. So I'm passing it a backend. I'm telling it where I want to run my circuits eventually. And this is important because not every backend is the same. Continuum's backends, we can, with the lasers, with the qubits we have and the lasers that we have, we can apply a certain set of gates known as our gate set. And Mikhail mentioned IBM. They can apply a different set of gates, and that's IBM's gate set. And so whenever we want to run a circuit or a program on a specific backend, we need to what's called transpile. You can also use the word compile, but we basically need to translate from whatever gate set we're in to the gate set of that specific hardware. And fortunately, you can do this within Enquanto. Enquanto handles it, or at least Ticket handles it on the underneath. And we'll show you that. So we've defined our backend. Again, it's the H2 emulator.
This is for any given emulator or for all emulators?
So all Quantinuum, well, actually, that's not 100% the case. For there are small differences between the gate set for Helios and the gate set for our previous generation of quantum computers. But generally, a gate set doesn't usually change from generation to generation within a company, right? So within Quantinuum, we have a gate set that has slightly changed with Helios. And within IBM, they might have different versions of emulation or hardware. So they have a number of different quantum chips, just like we do, and they have a number of different emulators, but they will all be running the same gate set. Does that make sense?
Yeah.
Yeah, great. So we're going to run a number of shots per circuit. Mikhail mentioned previously that we're working in a non-deterministic paradigm of computing here. And the other thing is, we mentioned noise, right? If we just run one shot, what happens if there was an error along the way, right? Can we actually know that there was an error? Can we correct that error? Well, that's not a problem that I'm going to exactly go into right now, but one to think about. And certainly, if you're interested in error correction, Guppy is a great language to jump into to start playing around with different ways of getting into error correction. We're defining a strategy of partitioning these Pauli strings. So I mentioned commuting sets. So we're putting sets of commuting Pauli strings together, and we need to pass the project reference, right? So we defined that we want these circuits to go to a specific project. Now here I'm pickling this protocol. I'm basically going to create different versions of it to show off some things in regards to compilation. But that's instantiating it and then building it given the specific computable you want to calculate. So again, we're looking at an expectation value and the parameters of the circuit that we calculated in the VQE calculation yesterday. So we've instantiated and built our protocol. We can have a look at the number of circuits that the protocol has partitioned our system into, and it's 3. And I'm just going to pull one of these circuits out. And it will look quite similar to our unsut circuit. So this is the representation of just the state, right? Whereas this is the state along with the extra gates required to represent the operator. And then also we should see at the end, it's in what's called a circuit box. Here we go. Some gates that look quite different to the rest. Hopefully you can see these look quite different. This symbol here is a measurement gate, and this is specifically in the Z basis, but we won't worry about that. But this is just a measurement gate. So we've applied all of the gates to create our state and apply our operator. When now we want to actually measure what happened along the way. And this is their representation. So now we have the measurement circuits ready to be executed on our back end. It's not letting me scroll anyway. But if you notice, I'm quite annoyed that this stupid hub cell is not letting me scroll. Anyway, you might notice that we've still got these H's, S's, and X's. Or actually, before we get to that, I'll quickly show you. You can also interrogate specifically how this protocol has partitioned these sets of Pauli strings, right? And what circuit index it's put the specific Pauli strings into. That's just something that might be more interesting. Some people might be more interested in if they're of the sort of chemistry background. So with those measurement circuits, we can now start executing, right? Well, not necessarily. As I mentioned before, we need to do some transpilation, right? These circuits up here are written in a particular gate set. We have some S gates, some H gates, some V gates, all that do different operations. We've even got some RZ gates. This is a rotation gate in the Z axis. And this is not actually the gate set that Quantinuum systems run on. So we need to do some compilation to compile our circuits into that gate set. And this is sort of the first point that Nexus comes in. Here I'm going to do a what's called compile circuits. So this is going to create a job on Nexus where the circuits will be compiled. And just very quickly showing off that Nexus itself or the Python package that allows you to interact with Nexus, which is called QNexus, allows you to do some handy things, right? So in order to keep track of specifically what jobs are running and give a bit more detail as to what the jobs are. So here I'm just very quickly naming this job. I'm calling it compile HEHP job because we're looking at helium hydride ion, and I'm going to run this cell. Now I realized that I shared my notebook, but what I'm going to do is I'm going to share my whole laptop screen because I want to. Great, can you guys see my whole screen?
Yeah.
Cool. So you can see the cell is still running. What it's doing is sending the job to Nexus. So Mikhail also showed this this dashboard. This is my dashboard when I logged in. Your dashboard will look a little bit different, but we can see the recent jobs here in the middle, and we can see a number of different tabs up here that we can jump into. I mentioned projects, right? This is where I can specifically go and look at all of the calculations I've submitted for one project, but I can very easily see some information about the job or the latest job that I've sent, right? So this is the compile job. It has been completed. We'll quickly just have a look at what information's in here. So there's a decent amount of information, and a lot of it's not so important. It really depends on how particular you are about the job you're running, but this is just an emulator job. We're not too worried about it. But one of the things we can do is we can come down here and look at the specific circuits or programs that we've submitted. So we can see that we've got our 3 circuits here. And we can look at what was submitted. So this looks quite similar to the circuit that I was visualizing in my notebook before. And we can see the set of gates that we used for this circuit, right? We can see some information about the circuit. But if we go look at the compilation result, there's the original circuit again, and this is the compiled result. So this looks quite different to the circuit that we originally set up. And this is because, as I mentioned, Quantinuum has its own gate set. And specifically, the 2-qubit gate of interest, which is most often the gate that we're most interested in, is this ZZ phase gate here. So if we look,
explain what you mean by you have your own gate set? So does that mean that because of the hardware you have access to some special operations in the ions that allow you to do, like I said, operations more efficiently? Is that the idea?
Exactly. So it's not necessarily that our gate set is great and efficient and the best. When we're looking at these circuits, we're thinking about an abstraction, right? These circuits sort of give us an idea of what might be applied in the actual physical quantum computer. But what's actually happening, as Mikhail mentioned in his talk, is, at least in our quantum computers, we're applying laser pulses to ions, right? To specifically affect the ion and get some specific state that we're interested in. And we know what that effect is mathematically, and we know how to implement it using the laser. But there are sometimes different ways of implementing the same operation, right? And certainly when you go from one architecture, for instance, the ion trap architecture that we have, to another architecture, the superconducting architecture that IBM has, there might be a different way, a different gate, a different operation that allows them to create the same state that we want. So these are different operations that ultimately have the same goal, right? And this purely comes from what can actually be implemented in the hardware. I saw someone put a chat down. Does that sort of answer your question?
Yes, yeah, that's great.
Great, cool. So Abdul asks, is the difference between the first circuit representation and the compiled version the same difference between assembly and binary and regular programming? That's a very good question. So
as in you have like high level instructions that translate to very specific, registers that you have to hit and signal on that very particular processor.
Yeah, I see what you mean. I'm not sure if I would make that exact comparison. I would say that the circuit, I think actually it's a good way of thinking about it, because there are, you have assembly, which isn't exactly what gets run, right? Machine code is what gets run. And the truth is we have these circuits, and each of these boxes, sorry, I'm just going to get rid of the chat. Each of these boxes sort of equates to some actual laser pulse that's applied. And in reality, there's obviously a classical computer in between that decides, okay, I've seen a ZZ phase gate. I know what a ZZ phase gate means. I'm going to tell the laser to apply this ZZ phase gate, right? So you can think about it that way, that it's sort of the transition from assembly to machine code, but there is still layers underneath. So it's important to be aware of that. Does that sort of answer your question?
Yeah, I see it's not a perfect analogy because with binary, like if it's literally just binary, you can't read that as instructions, but maybe different levels just above and just below assembly.
Yeah, something like that. Yeah.
I have a quick question.
Sure.
Is there any measurable difference between the two circuits, like at all?
So the aim is that there isn't. That's the aim. And in most cases, that is the case. And there are ways of confirming that, right? So you can just go through and apply these operations mathematically and check what the outcome is and make sure the outcomes are the same. Now, obviously, if you're trying to run this on a quantum computer, the whole idea is that you want to run something that's quite hard to actually do classically. So you're not going to usually be able to do that, right? That just defeats the purpose. The reality is that, for instance, especially in chemistry, we have these rotation gates, right? And sometimes we might have a controlled rotation gate. Now, these rotations can get very, 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 very minute. And that in itself, as a rotation gate, is very hard to implement. And then if you try to compile that into another gate set and represent that rotation in another, with another gate, it might be that you're not actually able to get that proper rotation, or you're not able to get that rotation to that specific decimal place. So the aim of good compilation is that these circuits are equivalent, and in this case, it's most likely that they are. But when you get to getting to quite complicated algorithms, quite complicated circuits, that starts to become a problem that you need to think about. Does that make sense?
Yeah, thank you.
No worries. Any other questions?
How many gates does the compiled circuit have?
The compiled circuit. Let's have a look. Hopefully I've actually already written it down or chucked it in code. Let's see. I've pulled. Okay, so I might have to add in a set here. I might need to. Sorry, give me 1 second. So OP type. Now, so I've pulled out one of the circuits. If you remember, we did 3 circuits. So I've pulled out one of the circuits here in this compiled circuit object. It should be it's a PyTicket circuit. That's great. Now, I think they have a N gates of type. Here we go. So as I mentioned before, we're most often, when we're looking at resources, interested in the 2-qubit gate, and the 2-qubit gate within Continuum's gate set is the ZZ phase gate. So let's try and see if we can, I think actually if we go ZZ phase, let's see if this runs. Great, 15. So we have 15 ZZ phase gates. I think I can probably quickly pull out the number of gates in general. In 1-qubit gates. 30. Okay, so there's 30 single qubit gates and 15 ZZ phase gates, right? So we've significantly changed the number of gates. And this is something to think about, right? Is like we've also gone from up here, we've got obviously a bit more than 30 single qubit gates to 30 single qubit gates. And this is, again, because in the active compilation, this is something that I haven't actually mentioned, sorry. And through the active compilation, we're able to apply compilation passes, which is basically searching through our circuit and looking for equalities, for instance. So we know that the mathematical object representing an X gate and a Y gate actually evaluates to a Z gate. So we're going to, instead of applying those 2 gates, apply the Z gate to some phase. And so we have a number of different simplifications we can make. And then it might be the case that, for instance, and I'm not sure if this is the case, but some combination of phased X gate and ZZ phase gate actually does the same thing as and this is a very contrived example and not actually true, but let's say it does the same thing as this block here, right? So it could be that a gate within one gate set can do a whole lot more than a gate within another gate set. Now, that doesn't mean that this circuit is necessarily cheaper to run. It depends a little bit on the cost of actually applying this ZZ phase gate. But generally, like I said, we look at the circuit resources for applying 2-qubit gates, because those are often the most expensive within the particular realm of, or within the particular gate set of the hardware or emulator. So, no worries. So we've compiled our circuits, so now they're actually ready to execute, right? They're actually ready for us to run them on some emulator or some hardware. And that's what we're going to do. And we're going to do this asynchronously because that's quite nice. Again, I've named my job here, and I'm just going to launch the circuits and send them off to Nexus, and I should be able to go back into Nexus to see that they're running. They're running here. And we can see that they're queued. Hopefully they won't take too long. But we can look at the programs, and we can actually, in the end, look at the outcomes as well. I think while this is running, it should take only a few seconds, but we will take the time to actually first show you how to access Enquanto, right? So you guys all hopefully have access to Nexus. If we didn't get your email and you haven't received an email about accessing Nexus, I will show you a QR code at the end of this slide that you can use to fill out a form requesting trial access. But here I'm just going to open up the same notebook server that Mikhail used. And the great thing about this notebook server is that it has Enquanto installed. It has Guppy installed as well. So you can run the Guppy notebooks that Mikhail showed you and walked through. And I apologize, I haven't sent these notebooks to you quite yet, but I will after today's session. But you can run these notebooks along with the tutorials that we have in our documentation. So I mentioned our documentation yesterday. It's got a number of manual pages which break down the different modules of Enquanto, but it also has a large number of tutorials which basically run through a bit of the theory behind the different things. So that, of course, this is VQE, and actually goes showing exactly how you might run a VQE calculation using the code. And so it's quite a useful resource for getting started with Enquanto and learning a little bit about quantum computational chemistry. So it looks like the lab's opened up. And I think in this example notebooks, yes, we can go into the Enquanto folder and we can see all of the tutorials. And in fact, I think this is the one that I opened up on the docs. So I can open this up. And you can actually just run them within this Jupyter environment, right? So quite handy to get up and running. The other thing is, if you want a bit of a quicker experience, you can also install Enquanto locally. So the installation instructions are in the dashboard. If we go down, you just simply copy these cells, run them sequentially, and you can copy your license key in order to run Enquanto locally. So are there any questions about that before I go back into the execution of the demo? No? Great. So we can see that my execute job here has completed. I think if I go into, I can look at actually the execution results. So I can see the specific measurement outcomes from running those circuits. And these will sort of have no inherent meaning or no, at least intuitive meaning because we don't fully understand the state that we've built with this circuit, right? The idea is that we've built a state that is incredibly hard to represent classically, and we are getting some measurement outcomes that Enquanto will basically ingest and allow us to analyze and give us some result. So we're going to do that. We're going to go back to my notebook. I can retrieve the results very quickly, and we can now use this evaluate expectation value method to get out an answer. So this is the energy that we calculated from our emulation, and we can compare it to what would have happened if we calculated the exact state vector with this whole protocol. And we can see that obviously these two numbers are not exactly the same. And how might we make these numbers better? We could increase the number of shots, right? We can increase the number of times that we're actually sampling. I will show after this next section, that we can apply some noise reduction techniques. Yeah, we can see basically compare how our calculation has gone. So that's, I guess, a little bit of the full integration with Nexus. The next two parts I want to get into are starting to look a little bit more into compilation, and then introduce a technique known as PMSV, which is a way of reducing the noise in our execution of our circuits. So do we have any questions at this point? No? Oh, yeah, go ahead.
Sorry. This may be a naive question, but the previous bar graph you showed with the most probable states, is there a way to intuitively map that to the actual energy value you get? Is the most probable one the energy value it gives you, and the other one contributes to the error, or is that not how I should be thinking about this?
I don't think there is an intuitive way of thinking about these results, at least in this example, when we're looking at chemistry. When you're doing a relatively simple algorithm, well, I say simple. So chemistry, we're taking a problem and we're representing it and then mapping it, and then playing around with the circuit to try and reduce the number of resources. This is basically changing the information in multiple different ways, right? And then through some clever post-processing, we're able to basically read that outcome and relate it to the energies of the orbitals that we first originally calculated classically, right? And this is what allows us to pull out that energy. So in this case, no, there's no real intuitive way.
Okay.
With other algorithms, with QPE, there are more intuitive ways. And in fact, this shot graph would give you an intuitive outcome that you could relate directly to the state that you're interested in. But in this case, no, that's not the case.
Okay.
Cool. All right. So what happens if we do some compilation a little bit differently? So as I mentioned, Enquanto is built on top of Ticket, and Ticket is a great software development kit in itself. It has a large set of compilation options, has been developed in-house in part by a compilation team that specifically tackles problems in compiling quantum circuits. And so they've put together some sort of default compilation passes. And previously, I didn't define specifically how I wanted the compilation to happen. So I just gave the compilation job a name. So it's just using the default compilation that's available. But we can start defining some more intense compilation. And I say intense, usually it will take computationally longer when you start doing more complex compilation passes. And we might notice this now. I've done it previously and it's executed quite quickly. Just because we've got relatively short circuits, the compilation can be done quite fast. But of course, if you start scaling up your circuits, then these compilation passes can take quite a decent amount of time. Looks like this job's being queued for a second. Sorry?
No, I don't think there was anybody.
Oh, okay. My bad. I'm hearing things. So while this runs, we're just increasing the complexity of the compilation that is done. And we can do it again to optimization level 3. Sorry, I don't know if you've realized, but this is how I'm actually increasing the complexity here. I'm just passing a new optimization level. So I'm just going to run the next one because it looks like the first one has completed, which is great.
Hey, Karen, I have a question real quick.
Sure.
So when I see this optimization level 2 and 3, this reminds me a lot of Qiskit. So should I think of it the same way in terms of that, with optimization level 2 here, that you are basically trying to reduce the number of CNOT gates, or in your case, MS gates, and then, with optimization level 3, you're trying to, change the qubit routing and mapping, things like this?
Yeah, so qubit routing is not really so generally, yes, you're right, exactly. Qubit routing is not necessarily a problem that the user needs to think about so much for our ion trap machines, because we have all-to-all connectivity. When it comes down to really fine details, you can start thinking about qubit routing if you really want to. But that's more of a problem for users of superconducting qubits, because they have to start thinking about, all right, well, because I can't move my qubits about, and I'm going to have to apply a number of swap gates to do some operations that are perhaps not very local, then I want to try and reduce those number of swap operations. So qubit routing is not a massive problem for us. It's something that is dealt with at the hardware level, and certainly something you can think about. And I'm not 100% sure if we have tools or if we allow access for users to start thinking about how qubits are actually routed on the chip. I can get back to you on that if you'd like, but yeah, that's not so much of a problem.
Okay, yeah, I guess I was thinking here that while you don't have to, you don't have to worry about the routing problem in the sense that of minimizing swap gates. You do longer range CNOT gates or longer range MS gates are more costly, and so if you need to, and you have to shuttling is also costly. So I'm just wondering if those types of things are handled with the new optimization levels, or is that something that is totally abstracted away from you?
Yeah, so that's abstracted away at this level. That's something that is optimized before the program or circuit gets run. So the actual routing, we have proprietary routing software that is done that does the routing specifically for, like you say, 2 qubit gates n qubit gates. And that's done under the hood. So this is more specifically, basically the simplification of gates based on the gate set, based on a number of different well-known patterns and approximations that can be applied for certain gates. Does that make sense?
Yep, thank you.
Here,
And actually,
are you
sorry.
Go ahead.
I will just say the specific passes that are applied and how those passes are defined is is explained in the PyTicket documentation. So if you are interested in really jumping into that, and actually the next thing I was going to show is that you can build your own passes as well. So if you don't want to use those default ones, you can build your own. Sorry, you were going to ask a question.
Yeah, so this compile circuits is effective. I mean, it's really like a compiler, right? Like Fortran 77. It's rewriting your code to some extent under the hood. You know, you could write a really inefficient circuit, and you're saying that this is going to take your circuit and figure out what is the most efficient set of logic operations that you're trying to accomplish. Are there bugs in this, right? Is this like still, you know, how like Fortran, they improved over the years, but, you know, is there an analogy? Or are these considered absolutely perfect? It's not going to mess up if you have like an if here, but you complicate it. How does that translate analogously?
No, that's an open problem. It's an open problem that people are working on daily, and we have people working on within the company. Of course, we the compilation passes that are built within Ticket are ones that are well known, well respected, well tested. There are some proprietary ones to do with our gate set. Well, not proprietary, but one that we've developed because of the restrictions, of our gate set. But it's an open problem, right? This hasn't fully been solved.
Thank you.
No worries. So I've done those compilation steps. The next thing I'm going to do is just very quickly compare. And again, this is only small. This is only a small example. So you can see the number of ZZ phase gates or the number of 2-qubit gates we have in this example. If we go from optimization level 1 is 15, 2 is 13, 3 is 10. Now that's a relatively linear relationship. That's not necessarily the case that it will happen in every case, right? And you can get much larger savings with much larger circuits because certain symmetries can be taken care of, lots of different things, but just demonstrating that this is actually working. And then, as I mentioned, also we can define our own passes. So here, again, I'm just using PyTicket, and I'm defining what's called a sequence pass. So a sequence pass says, all right, I want to do this pass first and then that pass next, or, you know, and a pass is really take the circuit, you know, the pass might have a set of rules that it deals with, and run through the circuit and apply that pass. So the first one is decomposed boxes. We came across a box before a while back, this one here, that had the measurement circuits in it. So in order to sort of increase the efficiency of representing these circuits, PyTicket does sometimes fold a set of gates into a box, and this obviously is not something that is run on the hardware. These need to be decomposed. That's what this does. And then Greedy Pauli Simp. And Greedy Pauli Simp basically is a routine that's been developed for simplifying Pauli strings or Pauli gates in a greedy way. So it really does its best to reduce the number of gates within the circuit. And so I can apply this pass using this pre-optimized passes option. And I should have had this running while I was talking through that. The things you learn, how to make things a bit more efficient. But anyway, while that runs, we only have 4 minutes left in my time slot. So I might not get to fully explaining and running through noise. But we did, obviously, I did show you that we're running on some noisy emulator. And of course, the hardware is also noisy. And so it's important that we start thinking about how we can mitigate that noise. And I mentioned that we could do that by reducing the number of 2-qubit gates. We can see that my compilation passes, my custom compilation passes is run. And you can see in this case, I'm actually able to get a more efficient circuit with my own set of compilation passes, right? So the defaults are there for general case. Sometimes you might be able to take advantage of specifics within your circuit. But I was mentioning, we have to start thinking about noise. And Nkonto has some methods for implementing noise mitigation techniques. Most often these are you have some prior knowledge about the system you're building or the circuits you're building. And so you know, for instance, that certain symmetries can't be broken. So for instance, in chemistry, if we're looking at a system with 6 electrons, we can't have a state that has 7 electrons. So if somehow a measurement finds that it's sitting with, it measures some state with 7 electrons, we can throw away that shot, right? We can throw away that shot because we know it's not physically correct. And so this is exactly what PMSV does. I should have executed this before coming to the call so you could see, but it does reduce the amount of noise and basically allows you to get closer to that perfect energy. Okay, so that brings me to the end of my demo. First of all, I want to say thank you for all of your attention. I'm happy to take some questions in the last couple of minutes, but thank you for all your attention and thank you for inviting us to come give you some demonstrations. And I will get these 2 notebooks to you in your hands so you can run through them yourself. But here's a QR code to our documentation, and if you haven't received a request to join Nexus, then you can actually use this Enquanto sign-up trial and we'll add you to the Nexus platform. So with that, does anybody have any questions?
Any questions? Okay.
I guess so. I understand that noise is a problem, but from the energy value you gave, the error was really small. So like,
Yeah.
Does that already have the noise included, or are there other sources of noise that add to that?
So this looks small. This looks small. For chemists, this is not small. This is very, very big. I realize that there's not a massive number of chemists in the audience. We care about processes that happen on very, very small energy scales. So yes, this is actually quite a big energy difference for us.
Okay.
Yeah. Sorry, I maybe should have made that a bit clearer, but yeah.
Yeah, no, that's great. Well, could you scroll down back to your QR code? I think we had some people that were taking.
Oh, of course. Sorry. Was that the
No
R's that
worries.
I heard?
We have a break now, so I don't know if you want to leave this up. But if
Yeah,
anyone
sure.
has any questions, I'll just, invite everyone, if you need to take a break, we have 15 minutes before we go to the brainstorming session, so feel free to take the break, and we have coffee outside. But otherwise, Kieran, thank you very much, and if anyone else has questions, please feel free to ask Kieran. Thank you, Kieran.
No problem. No problem. Thank you, everybody. I'll stick around for another 5 minutes with this up, and if you've got any questions, just feel free to yell.
Thank you. Steve? Yeah, I think we should get the emulator on. If we there's a great
That's true, but I'll say that there will be on interactions over there, there's a proprietary player. I mean, it's not, that's really good, right?
Yeah.
So they'll just be able to, they'll be able to like just run it and it'll get. Hopefully, they'll say, and it's okay, is it's like just getting comfortable.
Exactly.
But it won't actually give anything that's like relevant to how it actually works.
Is this what we did? Making you go.
Yeah, so I don't know where.
No, but couldn't you first, it'd be good if you had your own noise bomb, why don't you get it? And everyone would know your noise bomb.
Yes, I mean, well, this particular system, like, figure out what it does.
Yeah.
Steven saves, why don't you make a comment, we can.
Yeah, once.
Yeah.
Yeah.
Yeah. No, that's just the discussion. And then exactly.
Sorry, I was always.
How was the trip over this morning?
Oh, Very good.
Good. Well, if you come, what time would you come? 6?
Yeah.
7?
Oh, no, I think, do you know something? Yeah, yeah. Yeah, great job.
Pretty chill.
Yeah. Not a lot of traffic.
Maybe it's in that direction. If I have to go that direction at that time in the morning, it's very difficult.
Yeah, that's like one of the roads that feels like.
Yeah, and then you can just. Sensible.
I'm not certain. Whatever Google Maps does.
Right.
Oh, yeah. Yeah.
What do you see how you can map this, what you're doing? I think you always. But it's kind of what we're doing, so fast, but I'm just curious what your thoughts are.
Well, I think,
Yeah. I mean, I'm very new at APL, this is my 3rd week, so I have a very limited idea of what I'm doing anyway. It seems to be like what I think I expected coming into the conference, like what it could do. It's like that.
Like, are you thinking, like, would it be possible for you to do something like, I don't know if you have this, if it's APLY, but there's things Propel grants, right? There's all those things that stimulate your research, right? It's just, could this be a direction you pursue along with something in your, what you're currently working on? You see what I'm saying?
yeah, I think, might have to be a little bit on, but certain.
That's exactly what's going on.
Yeah.
I'm just curious what you're thinking.
Yeah, I think some of the stuff. Sorry, I'm tired. But, there is- yeah. Sorry, looking at it. I'm gonna look this up category.
I haven't used it. I've been through workshops with, I mean, I've used it through the workshops, but I ain't very. Yeah. Really trying to figure out how we, I mean, my materials, I feel like a lot of this is very relevant. Yeah, for sure. Yeah, it's all, you wanna, yeah, go ahead. Do you know how to sign it?
Yeah. You guys are right. Oh, yeah, great. I was gonna ask you a question. Sure. Maybe you know this. So, just like go with that. A lot of the stuff that Yogi does is similar to what Kid does. I think it's like. I mean.
Yeah, fair enough.
I mean, there
So-
are certain things I see that are, but there's
Yeah.
a lot of similarity. Right?
Definitely, yeah. So I mean, it's sort of productization, right? And seeing our needs to kind of link this up with the rest of the portfolio and the stack. As a company, there is strategic value in having your own things, so that's.
Right.
And,
But I'm also argue that for the community, it also makes things more challenging. You have multiple software packages that do the same thing, but those are the helpful ones.
Yeah. Yeah, that's something. No, that's application of that. The competition versus one like one other thing, like a monopolistic thing, right? And no, so for us, it's not we don't want to be dependent on it. On the technical level, at least how it was explained to me is that yeah, we wanted to address this to hold say the figures so it's a more complex, more complicated stuff. And yeah, we didn't have in the say trigger solutions, we haven't had any of these sort of condition offers.
Right, so why would we?
Yeah. And so the other aspect also, if you use a years, still almost. This was the same sort of. Yeah, it will be sort of hierarchical structures. I'm not sure what method. Yeah. Also.
And I kind of think the like inflation strategy. One from myself from that. But it's, yeah, I mean, I think it's challenging because from the user's perspective. But it's like the school, it's like every time you go to use a different hardware.
Yeah.
Language or nothing, it's like, and to some extent, you look at that, like, you go to use one versus the other.
Yeah.
Very similar.
Yeah, I mean, of course, there's some kind of sort of evolution and all of this, but it tries to solve the problem and these can send language. No, but I would say if there is like a consumer solution, then.
Yeah, yeah, I mean, I guess there's like a question of like should there be standardization? When should there be standardization? Yeah. How big is the constant?
And you will have the GT that will be ringing up with that's and now using that.
Or if I make other aspects.
You can have a transit.
Just offsets also these questions. It's like.
Some severe effects issues floating out into quality transferable debates because they are lots of size.
Well, that would be then like compiling bonds like enough, but then you have to
So it's important. I'm not sure why exactly, but
It'll probably help with the session coming up if we get it.
Oh, yeah, thank you.
Yeah, I mean, it's not a step, right? It's like, it's good because if you believe your hardware is better than
I would go.
go ahead.
You got one? You kept it?
You've heard.
Yes.
do it.
You sure you don't want to know?
Oh, sorry.
Some kind
Oh,
of. Like maybe there's a bit.
you're prepared, man. Go for it.
I think do a new hardware provider.
Yeah,
I guess
it's, I mean, for us on our circuits. It's a bit more down. Sorry.
Yeah,
No, for the number of arguments. It's usually once.
Yeah. I got all my calendar, all my notes, and a pocketbook. Also, like crazy full pockets, so that's also that's. Other small things you can get. Very, very specific. They're So then.
This is Greg, this is Tina. This comes. So,
I'm actually past that.
Go ahead.
All right, so let's get started with the final session here today. So we thought it would be good to kind of end it with the discussion of sort of applications. Everybody, as far as you've heard a bit about like the challenges in quantum computing yesterday, as well as sort of learned a little bit about quantum hardware today. You got a little bit more hands-on experience with quantum computing, how to code things up in languages. And so, now with this newfound knowledge, we would like to have a brainstorm session to talk about potential applications. Okay? And so what we're going to do is we're going to divide up into basically 3 groups here, depending on sort of how many people we may have in each one, based on these 3 categories. Now, if your application doesn't fit in one of these 3 categories, then I would say choose the one that's the closest you think to these 3 categories. One that's more maybe based in sort of physics. I'll say here, if you have like even things like so I'll just say here physics, any physics application that you may have, chemistry and material science, and then medicine and biology. Now, let's say that you have a problem which is like a combinatorial optimization problem, which is like let's say like a logistics problem or something like this that you want to solve, which is like totally not covered in either one of these. I would say for those folks, you might want to consider maybe joining the physics one. But I'll let you choose from there.
Roughly speaking, how's the breakup? So who would go to the physics? Okay, and then who would go to the chemistry, material science? All right, and then who's in medicine, bio? Okay, all right, we have people for everybody. I think it's okay.
All right. That works. Okay, so when you break into the groups, here's what I want you guys to think about. So these are the questions that you should be asking yourself. So the first thing is, what is the underlying computational problem that is sort of at the heart of your application? What are the methods that are currently being utilized for these systems or to solve these problems? And what are the existing bottlenecks that are typically there, right? Is it a problem where, we try to do, for example, at some point we have to do a simulation of the molecular system, and that's very time consuming because we can't model the entire system, things like this. The next thing is, because we know that we can't run, likely your applications are going to be very large, many different, or I'll say many variables that you have, and so you're not going to be able to run this anytime soon, at least say for the next year. On these quantum computers that Quantinuum or any other system would have. And so what we want to find are representative problems. So if you take your application, your interesting application, are there problems that are sort of much smaller that we can solve now, that you think would be interesting to solve now? And are those on the path of getting towards something truly interesting? For example, with a molecular problem, maybe you want to solve some large protein conformation problem that is hundreds of thousands of atoms or something, right? Clearly we can't do that now, but are there smaller problems that are on the order of tens of atoms that we can solve now that would be interesting? And if you can start there and start building up from there, that this would eventually get towards a problem that you really want to solve. Okay? And the last one here to think about is sort of what knowledge or resources would you need, do you think, right now, once you identified those subproblems? What resources would you need now in order to start immediately going after that, right? So like, let's say now, okay, I identified my smaller molecule, and now I want to go and try to investigate how to actually apply this problem to a quantum computer. What would you need basically to do this? Okay. Any questions about these questions?
How do you want to split the room?
I
I can go to the back.
Yeah, I guess maybe physics in the front, the material in the back, and then maybe over here in the on this side. The biometry, but okay. Good. I'll leave these up here.
Great, thank you.
Jordan said he's signed out. Where's he?
Uh-oh. I lost it. That's 95.
Okay, so who's for biology, medicine? Yeah, if your materials and chemistry come on back here. Anybody else? Yeah, okay, that's fine. Oh, it's okay. Yeah, that'd be great.
You should go.
Yeah, of course. No, it's free open space. Yeah, it's okay.
Physics.
We don't need to. Yeah.
If you'll have me.
I don't know. There's an application process. Yeah, I see.
We're happy with you actually.
So maybe a good place to start would be maybe introductions, who you are and what sort of things you're interested
So I think it'd be good if first we go around, my name is, we'll talk a little bit about.
My
despite your
background is
name, obviously, and then your background. What are some of the problems you think about day to day? You don't have to go into great detail, right? You don't have to. Think about where your thoughts are with your research, so we can get a sense of how you have background and things.
I do.
Yeah, I have
physics and,
radioactive materials discovery. I'm very interested in.
I'm Courtney.
Well,
I just joined
applications for
APL,
energy, so.
like 3 weeks ago, so I'm very new. My background is at PT in theoretical physics. I study spin qubit systems, the theoretical calculations for like that.
I'm practical switch. I'm at Ralph Performance Sustainable Energy and I'm my background is not aerospace engineering, but I work on my career.
Are you joining the physics?
Oh, yeah.
Okay, please go ahead.
Yeah, so my name is Shin and I'm from mechanical engineering and my research is from fluid dynamics, especially optimizing turbulence.
Yeah.
So actually, I'm not sure. Depending on what kind of specific topic, I can really relate quantum computing to turbulence or fluid.
Yeah, because then if you're pressing against it, like.
More Jackson, continue. My background is theory.
I'm Monish, I'm working my master's in data science right now. I actually work specifically graphite.
Yeah, like I'm most.
My
background is
JHU in scale. My background is so part of this is deciding finding applications, social application spaces, right? So one thing I did here, I heard at least two people mentioned computational fluid. It's actually started very briefly, right? So that's an interesting field, and I'll say here, I guess maybe that's a good place to start. Majority here. So there is a fair amount of work.
Excuse me, who's sitting here? Can we move this stuff?
I think that was, well, no, Courtney was sitting there earlier. I'm not sure. No, the other Courtney, Courtney with a K.
Yeah.
Different.
I'll move forward.
Is that?
more, real scale, like connecting the microservices.
So there's been a lot of work in this area where people are
Not
basically
that level, I still working on like
using
that,
sensor networks.
like that's
They take their problems and they're basically take some partial differential equation and map it to a sensor network problem. And then now what people are doing is basically they're taking these applications of the sensor network, turning them into operations. And the computer can run, and basically trying to do the simulation of the different on but using the sensor network representation is so the idea of doing partial differential equations on quantum computers is something that the question is there, and of course, it's, I'm not an expert in this stuff, but the question is really, what is the problem you're trying to solve? And are there interesting problems that you think that if one were to solve now, small scale, interesting to the computer, right? Something that effectively, since I guess we're talking about everybody here is very academic, looking at something that would lead to a high impact publication or something that the community would.
Broadly, if you call them off, I'm currently working on coordination polymer. And so basically asking the temperature in which the coordination polymer is there's some distortion in the solvent molecules mobilized. And so that causes an elongation along one of the coordination polymer, and that would be like translate to the strain on the
And you of course know how this strain.
Maybe I can ask a very more specific question. So, I mean, in CFD, people usually build millions of
like quantify that.
and I guess for current quantum computing, I think that's so
it's not we haven't actually
so I'm just
so we
curious
don't
how
quite know what the
how
value
can
is.
the quantum computer really
But that's something you could still
traditional or it's not
It's, I would describe it as a staple of current CFDs. So moving, if you're used to using sparse, algorithms that's tricks for the size that you on a traditional HPC.
that's trained then
You can't find that changes on computer and subset. So you need to find, basically look into your calculations and find bottlenecks that are focused on small subsets of things that are small, that are hard to calculate, and try to inject that into.
So do you have a sense of if you were to sort of, are you interested?
This is part of what I was
reading.
So have you looked into sort of the ways
doing
you can
continuous
do
things
this
on
out?
a quantum computer.
There's a
because
word, and you have a sense that maybe it's not working, or
number of qubits
scale or
and
stuff.
you only have typically things that
I
have.
don't know much
about
about
Means
computational.
that a lot.
So
A lot of what you will
it's
end up finding
probably
useful.
because like not so big,
The
it would be
a
kind of a
strategy
very
where
costly
using the quantum
computation.
computer as a system.
I don't know if this is, it might be.
Yeah, so
ignorant,
what you
it might
usually
be-
do is try to trace them from you're looking
Right.
for some
Could be interface.
you're looking to where does the excitation happening, how local is it? It can be that this.
Is that the same issue for optimization? Like you cannot really represent all the parameters into the qubits.
So if you're talking about very large optimization problems,
That's strongly
same thing.
system.
So
Generally,
so it seems to me that it's easier to do some
where's this most likely
more
to happen, right?
stochastic related draw onto value
So where a quantum computer really has a lot of advantage of physics are in things like magnetic systems, real time, like things where you have what are called sine problems, where you have highly oscillatory systems, and like let's say you're trying to integrate that, and basically because of the nature of quantum computing, kind of sidestep that integration part of the
classical simulation.
and like get the answer out of the happens so a lot of the advantage of quantum computer physics context comes from knowing how to map your state. And then also finding problems where there is a low overhead because of mapping of the problem to the qubit system. So that's why like magnetic things map well, is because it's up and down, right? So they map very well, whereas if you're trying to do like a state system, like 23, that you have a fair amount of overhead just mapping that into the qubit system. Should really put really special problems.
It's actually for small.
It's all lots of as is usual with physics. It's a lot of the awful details.
Then depends on the study. So what do you want to do out of this? Something
Well, I would say
I'm not an expert in this. I don't know if you know what your current progress. I mean, all I can say that they've solved some small problems. For example, in like things like Burger's equations, things like this. They've looked at obvious scopes would be like really where we would go. But I know things like Burger's equations have been advice.
If you're talking about like just looking at algorithms for actual quantum computer, there are a number of different approaches that are used. Translation of traditional matrix tensor representations. There are also what I would refer to as like type representations which can actually map the quantum system onto classical mechanics and then use the classical mechanics
When you
yes, to do
math
whatever.
calculations, your basis scales the volume.
Yeah, he's at Dartmouth now. Yeah, there's a guy at Dartmouth who was coached from.
That can be very limiting. So maybe it's
Giannatis, I think, I forget his last son. Yeah, he's in the math.
So how far
okay, let me. I have been working on into the materials I want to get. I've been working on this energetics, I found that the first challenge comes here that we have to transform or map our say fluid dynamics equation towards something like the Schrodinger equation. Then you can you can generate the Hamiltonian wave function. Yes, for example, we can stay for the recent work I am working on is we're trying to do some amplitude encoding.
What's interesting, right?
So we have in CFD also knows very well that whenever we try to resolve, if we want to resolve the small scale information, then like we get limited with the computational resources. So here, what we did actually, like we are working with the very small problems execution like that or process flow relations. So there actually what we did like for the variables we normalize them so that we can consider them their values as a probability because the assumption has to be 1 and the equation, the dynamics of the dynamics which will take us to the next step of the state of this variable. What would be your velocity? We actually working with LVM, so our variables are
for example, understanding the vibration distribution. Depends on the system. Is it a strong?
So
and again,
we are creating from those equations, we are creating a matrix vector representation.
If the system is
And,
strongly correlated,
like,
we probably want
now
those effects.
our matrix has
Exactly,
become
that's
our
what I meant.
operator.
Yeah.
If we want to implement that in quantum technique, then there are some requirements that it has to be non-preserving, it has to be unitary. And so I'm following a work and they have proposed some way like doing some similar value composition, some linear combination of unitaries and all that. They have from the very big matrix, solution matrix, using those techniques, they do some combination of matrix. And finally, they are becoming unitary.
The way I think about
They are becoming the operator we require, but they are not the standard operator like we found
in terms of
not gay.
how do we understand the electrons? Are the electrons?
But it's still like when we can manage to get those operators, that we can manage to fulfill those requirements of unitarity and others, then we have tried using those on the Qiskit simulator.
What node am I in right now?
Like maybe I don't know much. Maybe at the back end of the Qiskit simulator, it is breaking down those operators into standard gates, and finally we are achieving some
Right, so like if you're taking
and
that
as it is a simulator, we don't have
issues
issues of noise and all
inside
that.
of one computer.
But there
you
are
don't have to
some
worry about it,
numerical
right? Then you just measure
because
your downward
we are
and you're
actually
good.
scaling down our
Whereas,
variables
if you actually just want to get that
to
entire
do the
measurement
amplitude
down, you
encoding,
still have to pay
and
attention.
after
And then the
the
other thing,
complex
of course,
circuit,
is
we
that,
are extracting back and again
the
multiplying with
accuracy, right? So, I mean,
the
DFT, for
factor
example,
so that
has
we can
this
get back to our macroscopic variables.
Since
So for those
you're interacting with light,
process, we are having little bit errors, but
modeling that.
it was working
And
good.
one of the ways to fix this is to go to higher levels of accuracy. So, for example, DMFT is another.
Yeah, I think, you know, the compilation problem you're talking
There are,
about is
there are
sort
already
of like
algorithms that exist.
that's
that can
to
monitor
some extent, that's sort of an afterthought, because that means that you've gotten to the point now where you at least have a quantum system, right?
Yes.
And so you kind of solved, I'd say, half the problem is just getting the application down to quantum searching, right?
And also, there is another problem. Like,
Yeah, I took my steps up there.
each after your science test, you have to
Yeah.
system and we will have to do some classical manipulation on that. Then we can re-encode for the next system. It is a limitation because it maybe for quantum hardware, actual quantum hardware, it will be costly. Because if you need to go through 1,000 iterations, then it would be better if you do the 1,000 iterations and then take out
We collaborate a lot with.
each iteration
Oh,
to
yes.
go through those measurements.
I
In simulator it is fine because in simulator we can extract those direct value. We have the access to those values from the state vector itself. But in real hardware, when you do the measurement, it will give you only single state. So to know about the probability, to know about
Okay,
the
so-
values of the
So, okay, I've been working on
specific
actually
variables,
getting the
then you have
structure
to,
together.
he might need to
forming
make
that
millions of
structure.
measurements to
And
come
so,
up with the
once
okay,
I
which
get
is
that, I would
I mean,
need
which
to do
state
some
is having
non-luminescence,
issues.
so
That probability is
photoluminescence
the value for us.
measurements. And
In
so
reality, like,
I would guess
probability is the
based
value of
on
our
that, then I
or
would
maybe
like
the
go
temperature.
into some
You
calculations
amplitude
to know what
code,
the
so
better
you
structure
can
would
get the
like.
velocity
But
vector.
and also we are having another limitations like
From
non-linearity is a big issue. Because people are, I mean, some workers.
We've done
use
monolinear
CFD.
TMDs,
They
not
proposed
the
Karman
radiation.
linearity technique,
Because
that actually
they grow
increases
in
the
bulk,
version
and
of
I've been trying to
Sure,
expose
I mean, you can
lots of problems.
linearize
So
a
I
nonlinear
would get
equation,
more,
but
but not yet.
That's
it will increase the number of variables because of the polynomials, lots of polynomials.
Like ideally,
So, yeah, they did some work for very small problem and they truncated the polynomials up to second order. And like still it is in a stage like
Yeah.
everyone is trying to propose some way, trying to get rid of those limitations.
Yeah, but so this can be done with
Right.
Monte Carlo.
Yeah, Yeah, so.
Oh, very interesting, so you.
Yeah, I think this, the problem you're talking about of like having to do a lot of sampling. and sort of
Okay,
first
so
sort of
I came
operation,
here
you have
not
to-
knowing
I mean,
anything about
that's,
quantum
you know,
computing.
uh,
All I knew was like superconductivity.
that is a
That's
model
what
that
you
I
learn
would
in
say is a good
chemistry.
starting.
So I
It's a
didn't
starting
really
point to,
know
like,
what it,
yeah,
like
I
quantum
guess to say that
computing.
to be able to get to the
fully
point where you
entails,
could potentially
and I
run
feel
the
like here I learned
algorithm,
it's
right?
way
Even
more
if you
broad
have to run
than
the
what I thought it
measurements,
was.
that's a good place to start because now that you're.
So I'm like
baseline,
slowly
right?
kind of
So
learning about how
there, you
it
now have
all
to,
works.
you have to, you have.
And I had
it's like
not
tuning,
realized
but
it
at
was
least at that
more,
point, you
you
have
know,
something that you can.
more
affect
computational
right?
than I thought.
Yeah, and
I guess
also
it's like-
some researchers they are trying to find some way if we can directly transform the equation towards like a Schrodinger equation. Then it will be easier to
So query operators
like
nonlinearity
is really
does fit into this, right? It's due to that query operation as well.
The linkers
now some continuum components.
The purpose of the is basically always.
And then similarly, there's your data.
Yeah, so I mean, what I guess, what I'll say is I think that
It's you have something that you're trying.
the things like the CFD calculations, I think that they are, it's an interesting place to try, right? Because you have to remember again, nonlinearity is going to be a problem. So then what can you do with a linear problem here and what would be an interesting problem to identify. Part of this, it's hard to, it's hard to identify specific problem. We have to go through the literature, right, and see sort of what people have done with it. But I guess if anything, you need to know the parameters, right? Which is small problem, and also.
You have to first figure that is the macro.
Actually, I'm curious how people do or how people use quantum computing for
Yes,
like
right now
how many actual
actually
molecules they have.
states
What kind of can they really like simulate a real different
around 100
or it's very downscale to one or two
this
how they really
So I don't know enough about how the training method. It's kind of ironic. I know a lot about.
And is it a easy match or
I can't talk about
Different.
We were stuck.
the noisy match requires right like
this is a
99%
so
because like here's
it's a lot of
tweak to make.
what they end up doing, which has similar equations to Hermitian
It's
a lot of
Oh, it didn't work.
you take the stochastic equation,
When you look at this,
change it into a form that maps onto a real-time Schrodinger equation.
or it's extremely demanding in the sense.
Exactly, and then at the end, you post-process it needs the result that you get.
Yeah, we translate this
Expand into something that's meaningful to your
Often,
that would be probably how, like, this would be your work as well.
I was.
Same, it's the same principle.
Had a nice picture of this, right? Still have it on.
So
Very good shots again. So the site.
Yeah.
So how does that, is that
Not
all
doing
solved?
That's not. You're doing physics math.
That's, yeah, the end of the day, you're running this experiment.
Some sort of.
As a real expert. Approximately like.
So you have to
Base pair is about 250.
or whatever. It's very much that same.
Yeah, there are arrows. It's 80, so you have an effective arrow power. 300 volts.
Yeah, usually with the simulations, it's not like, I mean, I don't know if I call them molecular dynamics, doing it.
Well, no, oh, yeah,
Like
it's-
molecular systems.
It's not, if you're asking, am I gonna get 60 particles that we can the 20 million or whatever it is?
And I also
No, you're gonna get.
at a distance problem is relevant for genomics.
The difference is that, if you need to simulate more quantum chemical effects, then
You have to string, the question is basically like, are these
Really
all
what it
just the
is
same, like are these
that,
within sort of
you
finding
things
each
last
other
week
in some way,
yesterday,
right?
maybe
Like,
this all here, but
really do is
when you simulate this class,
there's like a dynamic programming approach, but it's still n squared consequences. It's kind of not to say my way around that, but there's a hypothesis, right?
And that's costly.
That
That
is
is, and the thing is, you can take that exponentiated matrix and represent it in terms of these gates. And so then there's like no exponentiation.
I mean
the series of gate operations
I
that
might
I'm
be
talking
more
about.
that period operation, if I have straight strings, I wanna check
So
whether
that's
that's
where
very
the part of the string simulation comes into
Be
play.
under some
Usually
metric
you take what it means, let's say you had some e to the
Right.
minus int that you wanted to simulate over some period of time.
Not the database, it's just the two, my two strings of length n.
Propagate this.
Yes, then you have to.
So you still have to, choose the observable where you measure. You still have to decide on what measurements you're interested in. And so that's going to dictate sort of what you do at the end. It's obviously, but assuming you know exactly what you want out of it, then you can choose that at the end. You just, again, you have to sample, but you can get the probability distribution that you're looking for.
And then, of course, it's not perfect because it's not in there.
Usually the problem there is the size of the system and then also what type of interaction. If you need a lot of interactions in your system, highly non-local, that corresponds to greater non-locality in the gates that you put. And so that means that you have to solve now the problem of compilation down to the gates that you match. So it increases the most
semantic similarity.
Even in the case of one, what do it happen in the compiler?
Right, to what extent they find is a measure of that, like immediately else linked distance, something else may have a chance.
I'd love to know a little bit more about your whole theory.
Yeah, well, the shot is, it's in the QE.
I guess so. The thing that I thought of when optimization was said is a lot of what we do, at least in my collaboration, is like really large fits either on large amounts of data or with a lot of different parameters. So I wondered if this could like optimize like a second differential equation with a matrix. I thought that would be cool to try to apply. I don't really, the way I do this now is like on a classical computer, you say, okay, I have all these parameters. Can you
What is the
give me the best set of parameters? I don't know how I could map all of those parameters. That's fair, yeah.
Initial approach would probably be with
So
that.
looking at how to get the meanings of two tests.
But we can think of a logic to
this low,
two or more
lower parameter.
physical fields, like geometry translating
Sort of real time.
But yes,
I
I
don't
know,
have
because of
this.
So what you try is to stabilize it on
That's a problem.
I'm an undergrad freshman, I'm majoring in finance.
Oh, I
Yeah.
see.
So,
Trying
trying to keep it
Okay.
problem as close to the original one. Usually you go back.
One can periodically measure the particularly measure operators.
How do I calculate
The overhead.
Crazy to.
And then you get
We can talk about asymptotics, which is like 5, 10, 12 years out, the asymptotics.
I guess so.
If they don't commit.
The problems I would like, an example is like, I'm on a neutrino elevated case. The fits I do are usually like huge amounts of parameters, but what other people in my collaboration do are like unbin fits, so they just have ever increasing amounts of data, so it's not necessarily.
Well, so.
Sure,
dealing
but
with
even-
data on a quantum computer, just because it's really slow to load it.
And in between
So try to.
Right, I guess even if I want a sort of viable instant reporting. I think it's fine with it.
So, same way.
We already have like tiny
So how, I think that.
Understand what
I remember coming to shows between the operators.
Try to find
That's the
those
say
small
operations.
data problems that
Yeah,
are huge
but I never
complications.
understood how
Yes.
we're mapping that to like a laser pulse. I
So,
can say that this is.
once that problem.
totally different topic.
Make sure to
Oh, okay,
And
okay.
then,
Source is
no, but the,
Yeah.
This is just from.
More efficient computer.
there is some like really fun.
What would
algebra in there.
How would like one
stabilizers and
event in data Like, would it have to be one event is one qubit or?
It would be, you know.
When not, we're talking about large amounts of data.
It could be, so like, okay, so with large amounts of data, it would be, so it would be like, oh, maybe there is an area of this
So this is
curve
like the
where that'll try to,
layer.
where it has tortured topology and all of my methods.
I think I'm angling between sort of
Right.
the
And then
dashboards,
topological data analysis might be really good to response to it.
doing some database services, right? So it's like, well, you know, maybe like a database structured in this very particular way.
But
Here's a database
if
with
you're
like
talking
1,000 things in it,
I
500
have,
right? And like this program
really good
runs at least in a couple months.
7 million.
That kind of a thing, where it's not to
40
the instant size where we start caring about the whole world. Right,
Each
but it is to the
one.
point of like, and yeah, you start with
So do you
like
think that-
coding times, decoding times, get over the, you know, get way too big for
So,
you.
sorry,
The point is, you can say like, here's a toy
So
thing.
the optimization
where you can
problem,
start-
the optimization problem you're trying to
It
solve.
does seem like the over.
Yeah,
right?
So what if this,
So
so
maybe it's for the moment, this extra thing.
So,
If your thing is exponential, you know.
say a little bit more about
So
what is
That's the
the,
bet.
but yeah, I guess,
Then there's
how
no
does this work? So how do you get to the point of
So for the stuff I do say, we have like
At the same time, they are
about 1,000
topologically
crystals,
right?
and each crystal has some amount of data set, and each
format.
crystal is also going to have a different like model, and we want to try to find the best like parameters to describe the model, say if it's a line or if it's a sinus fit or something like that. So to me, I guess that curve I'm trying to fit for is given all of the possibilities of values that could describe the sinus wave.
So there's, of course.
What's the best one? And the optimization problem made me think of that just because like they showed an actual curve finding the global minima from that. So I wondered if like each parameter would be a qubit that it was optimizing for, or how that would happen.
Yeah, I mean, it usually is the case that if the number of variables or the number of qubits that you need. Yeah, I mean, it depends on how you decide to solve the problem.
Advantages then.
If you wanted to go with like the
But your point is
variational
generally
type
not,
of problem,
which
you
I think
have to be able to map
Yeah,
that out
that's general.
to a
So,
sizing model.
no, sorry. For
If
any,
you try to go more traditional with like.
It's not
any, yeah, any
Line
non-star,
algorithms,
right, because the
you're gonna need to
concept
find
is,
what's
when I'm
called
saying generally, I mean like.
which is basically like
what is
a series of gate operations that
Yes,
is
your
able to
point
like
is your
identify,
caveat.
I'll say recognize solutions, but not, doesn't know.
So I guess more
Know the answer, just could say, verify, yes, that's the right? And so,
But technically,
the
it's
latter is much
we are
harder
now
on
made
the
an informed
former
decision.
can
You
be
just
difficult
down
if
query
you.
So that you
So,
don't have that
Yeah,
interaction.
taking basic
No,
results
it's just
of
like on the
having
layer.
nonlinear, or you have like
right,
you map it down,
It's like
you have many different non-local interactions that you describe this.
What we want to show is our.
That's
So it kind of happens that you have to.
You're not gonna win.
I-
So we focus on
Whereas,
that.
What the thing.
at least I
But
think it's a
let's say it's, the main question is what the.
But
It's
Okay.
very low.
you know, I guess,
You directly.
I don't know
the state
much
the graph and the
One
coin.
applications,
you're off to the
which.
Like there isn't.
your problem.
We believe are.
If anything,
Classification.
the operator like for actually
Yeah, when I think of like curve filtering, I also think of it.
much.
That's why we think that.
Communication operations
And then
like
we
that.
just.
But it
When
doesn't
Aggregate
figure out-
complicated,
Yeah, I
but it
can
seems maybe
tell
more
you
natural,
that.
if that makes sense.
In
Right.
I wouldn't think so immediately there, like part of what I
Yes.
was interested in
Yeah.
this workshop was just to
And,
see how
So,
this stuff could be applied.
Yeah.
And there's other things you can do
There's
that might be faster training and stuff, but I guess it's just I'm used to thinking on like one, I guess, say, I don't know, particle interaction or factors or one event. So I'm having a hard time figuring out what mapping is. It sounds like that's the translation. For
We know
like
this
each
model is
specific
not-
tailor,
or,
probably have to figure out a way to like
Right.
use
More
the
like a
dimensions.
long-term
Yeah.
solutions, of course.
Although it's not the same as the classical.
Yeah, yeah, no,
We
that's.
want to kind of.
If you're trying to use
can do
things
things
like
It would
that,
be more
it's
for
classical,
like
the quantum
kind
walk
of
will
to
spread
figure
out.
out.
Yeah, I mean,
It's a square root.
We've done
we
some
know
work
what
before
we're
where we
missing.
looked at like
Yeah.
particle tracking events.
And so the idea is
particle
we
data that like
have
try
just
to
a step operator, which advantage
classify,
the graph is a coin operator flip to tell you where it's at.
Quick,
And that coin
quick interruption if it's okay. I think, by the way, lunch is ready. I imagine some of us are hungry. So why don't, if it's okay with the leaders, can we stay and just get food? Yeah, let's do that. So, we'll do it by team. Let's have the physics team go first. And then so then I'll.
we're better.
and flip operator.
Right.
So you're this is without some makes it sort of like heads. Of course, and when you use a step operator, you have basically for the two-sided two options. Where it is regular graph. So at every node there are two outgoing edges, right? And so being able to number them somehow. I say or I'd say and then now that you're in that the two states, the coin flip happens again, have more dates, now you're in 4 states. Because you could be each of those nodes and you can have a coin flip each of those ways. And every time you take a step, you're doubling the size and evolve the way you're doubling this this lets you explore the graph faster. And at the end, you sample what state you're in, not necessarily times. You recover a distribution of the final.
Right.
This is just big, it's multiple. So that's the rough.
Yeah.
The rocket system the language processing.
That's right.
How to manage favorite for these types of systems. Semantic similarities. Right?
Oh, you have the interface, right? You don't have any K.
That's
probably what you did can be. Well, I don't know, but sorry.
Yeah, that's kind of.
Yeah, you have.
That's what I was
getting.
Yeah, that's why I wanted to know what the problem
So
was.
usually, because you're not for that, the way they're wave vector.
Yeah, cause this is like, this, and I was talking about this all the time, this is what we literally did for
So when you have,
So Dave and I worked
the way I
with
teach it is-
Clover and Red.
music,
As a
I know that music is like vibrating atoms.
And
Space is
we
vibrating.
were trying
the air,
to use
that's how
what they had
it's
done
right
for PIR.
And so all
It's
of
kind
these
of like a similar
vibrations, they
process,
have
it was a really good search, and it's a lot simpler
like sine wave.
than like what you were saying earlier, I missed the.
So all these sine waves have different frequencies.
But what you were saying
One way to
earlier
think about it.
about
So
the
sine wave is infinitely periodic.
So
This has
protein
one
docking.
frequency. So we know that
That
sound
seems
works many things. We can plot the genomic as frequency
Yeah.
5, 10, whatever it is.
Yeah.
The relationship between sine wave and
and
frequency space.
space.
Called reciprocal space.
We found it
And
fairly.
when you look at the units.
Like a lot simpler than.
Sine in the sine space.
Earlier, just in terms of like the operations that
Or
you're.
in, sorry, in that case, this
I don't know if the exact translation.
the crystal space. And then you go to the reciprocal space,
Yeah, I
which is the
feel like
frequency
I
space, and that's the hertz.
But I feel like.
Right, hertz is measured in frequency.
Yeah.
Units
That's
is
to
watt
be
over second.
down your problem, right?
Yeah,
It's
so
not like.
The
you're
the
looking
thing that is periodic thing.
Like the graph that you
It's
worked to,
time.
like the
That's how
small.
we talk about
subset
music,
of
but music has a certain.
Yeah, I
this
wonder even.
wave, right?
If you have.
Yeah.
Is it?
Yeah.
It's sort of like a male
So in
female.
the crystals, we do the same
The
thing,
idea-
except that the periodic is space. So the crystal is infinitely
But if
periodic.
you took all of the
So how do I
things you
relate that
ran
information?
variants, is there some sense of like, well, these two things are similar,
Professor Scheller.
right?
Daniel
Like, there's some sort of like continuum of moving from spot to spot, where you can start to say like,
Yeah,
these two are
just,
similar, so it's just, you know, sort of dark dog is this one, maybe probably dark dog is this kind of thing.
Have you better?
Yeah, I have better. I've after a couple times, never got physics for faculty meetings.
Oh, fine. Oh, that's fun.
This small object is going to exactly match the thing. That is the simplest problem in thinking. Not something to any point. I just think.
Right.
Yeah. So you'll get answer.
So I wonder if
It
it's.
fits. For playing and
Is there something with
They are using the
this potato?
Sure. But that comes down to an intermediate representation at some point, that like is instructions that go to that to the.
It's not that, it's more of a, I think it's.
Yeah, no, I see where you're going.
Right, but I'm not talking about that. So, I mean, Qiskit actually is not just about Qiskit is also builds the simply language instructions that actually get sent to the hardware, right? But you can take and then the genomic one build out straightforward circuits. Yeah, you can build or other types of architectures. These still have because it's set on top of it, right? So the point is more about the language itself, right? Like defining circuits, right? Actually writing out the circuit.
And maybe that's where
that Qiskit has done does well. You know, and there's Honeyland, which is part of Xanadu, which is they also have their version of Language too, right? Which is like it's distinctive anyway, right? It's more geared towards machine learning techniques, but it's still
here's it down this number. Right then classically guess and check.
Google has
search, right? Picking helps direct.
That other type of language that's very similar structure.
You know,
the quantum. So everybody's building out their own version, right? Kind of insane.
Yeah,
at least in Detroit. But there are certain things like I think with Continuum actually I guess there's a bunch of proprietary stuff in there that is not with that is not with Anylane, that is not with CERN. Because all of those are like open, completely open. So that is the one thing I can point to where I'm like, okay, I can see I didn't like, but generally speaking, there's high degree of overlap in the circuit architecture. Sorry to catch you mid bite on the
Right.
So yeah, surely once you go down.
We are two.
Down lower than that.
Please, don't worry.
There has to be a way to put it into instructions.
We'll get it. Food is something that's generally there.
Yeah,
So
no,
very
this
few
is-
opportunities.
This is something that you've been thinking about for a while, which is like when using a quantum computer for one of these approximate searches, like the quality of the results.
Where's Adam? We have to see how he feels about.
Like to what extent can we leverage that?
To get on a call real quick, get your huge matrix down to a bunch of
Like when doing quantum
linear
you don't
ones.
get the same distribution.
How much is that like?
Is that full? Like is that?
How much of your work is spent on that? Since I don't think that would take a long time to do. Like, is there a lot more processing you need to do?
Could it take to
Or
run
you should-
a separate
Actually, even
if
quantum.
Gamma used to be important when you had a computer that
For
the
our
gamma point
numerical
or not having gamma
we
point.
have partially
Convention is
compensation.
much larger, not larger, but it's more time.
Which we
These
can't
days, the gamma
solve
was, no gamma, it's just.
So we then
Not-
on to numerical.
Not really, but you won't
The
notice.
numerical technique can always discretize that equation in such a way that
The computation
come
won't
up
come
with a set of
more
linear
expensive. You won't
I
notice.
see,
it.
okay.
So then we can like make it a form of matrix vector.
You won't notice it.
That's what we already do even before.
Oh, sorry, gamma only versus
Now
gamma.
we
short.
go
We're talking about
trying to
I'm going to share with,
If you look at this.
do the step-by-step calculation instead of in classical computation.
Yeah,
I see.
on the
Okay.
quantum computer,
Take it out and.
you will need to do similar things.
This is
on last.
Yeah.
So you would come up with a clever way and
Yeah, so the CRISPR is the general.
leverage.
For doing gene. What we did is, so there's the associative memory model. Say basically like a class.
This is pretty cool. You basically continue your PhD.
So then they
So
do
now you're just earning more money.
You can
Cool.
give it a bunch of data.
In between that.
Well, no, because what I think is interesting, right, is, I mean,
You
you're
give it a bunch
talking
of data, at some point, you give it like, you give it too much data, and basically, what's happening is, okay, so almost, think of it sort of like a ring, where every point
Of course,
every
come on,
data
of
element
course.
right?
There's
Let's
a-
say working with the first couple of years of
Right, 'cause I think
a very
it's
small
like-
spin-off.
If you too many measures,
Rounding over
sort of like, it's the like.
When you say memory.
arbitrarily
Yeah,
complicated.
like, so
That
this
was
is think of it as like a part of.
What is very cool.
Those are gonna
And
kill.
so you have different ones
Anything
that you
for-
are going to say this is a muon.
No, I was
So
wondering,
far
so
into
I was
that,
like- I've always
So
said I
how do
want
you-
to like.
how do you
put
find
a
bunch of these
very
memory
intellectually
And-
close quantum
But like,
mechanics
I've never
that you
been,
work really well and
there
nicely
on
on
the
quantum
top
effective
in
training.
industry, I would
And
say.
If you put too many,
And so when
then
you
the
were
memories can
showing
get
the
too close to each
different
other, so then you can start to
cases
misremember.
you worked on, that's when I realized
So
how
it's equivalent to
similar
like, you know,
of a
you
work
being
I
like,
could
yeah, I'm
do
pretty sure I was
if I
here
go
when this
into
happened,
R&D
no, you
and
weren't, right? So
Yeah.
same thing where it
And
can
I
say,
was
I'm
like,
pretty
okay,
sure
so
this
I
is an
could
electron,
actually
just
do
like
what I like
just
doing,
because the sort of
and earn more money.
yeah, it is, but it's like a sort of
I still like
fear of
this.
like
The research looks
basically,
different.
if you start to say this.
Okay.
And on
Probably you get
classical
the-
memory model,
Yeah.
these things
Yeah.
grow exponentially.
Yeah.
And we were trying to see on whether or not in the
Yeah, I
quantum
feel
case,
like
whether or
you
not
would
that still
have,
happens.
you're more
Whether we
constrained
get
as
more
to
out
what.
of it.
There is a lot of, let's say,
It seemed that
external strange things that
get a little bit more out of it.
Yeah.
Empirically, we can see that this is the case, that we can store more memories.
Yeah.
even in classical.
Yeah, you need
what I was
to.
talking
Yeah.
So this kind of is like an alternative form of
Let's
potential
say not
advantage.
the
A lot of for toy problem, like it is more problems for AI.
I mean, this is the
something,
inside quantum.
you know,
Yeah,
you
many
can
of
see that
components
there's
since being
you know, the quantum processor actually
applied to classical computing.
Yeah,
Basically,
it
it's
seems like you can store more
if you
memories
have that,
than
like,
classically.
sparse, then you end up with
Yeah,
like
so getting a little bit of But it's not significant.
right? And that's
60%
increasing to extra parts on
I
our
see.
right? But a
How
lot
does
of
the math
other
make
approaches,
this? Because again, I think now like one memory is one cube. Is that not the case? Like,
No, so we actually have
those other ones have
to,
been
we
manifest. They've been
basically created a grid.
Turns out that
And sort of the particle, like whether or not there is a
right. So
one
that
or
that
zero.
sparseness and well conditioned helps. I think it also prerequisite. Also, there's there's that
Whether or
issue with
not
encoding in
that
and
determinant
detriment because you don't get the full
I
result
see.
out. You
You
only get
have
out
a series like a, you know,
bits and
track,
pieces of the
right?
vector, and
You
you
get
get
that
that
track
vector
in
to
this
keep
like
doing
this
measurements.
2D grid, you don't
kind
have
of
that. It's
it's
not the,
right. We're like we're covered.
it's definitely not the smartest way to do it. It's just a way to feel.
I've also heard some
Okay.
quantum machine stuff like very specific small units. But real functional problems are.
So the thing is like, even if we think about a single qubit, say initially we have its probability of 0 and 1, 50%, 50%, but maybe in next time step, after doing some manipulation, where it's, our expected probability should be 75% and 25%. Another thing is, in hardware, like, if I do the manipulation, if I do the measurement, I will
Yeah,
get
because there's
only
of
one,
course not
the
the
one
experiment for this.
Now, maybe I will do 100 repeated measurements. Then I might find, okay, the zero is coming 72 times, and the one is coming 28 times. But still, we are,
Because we
you know,
don't
I mean, we're getting close, but we are still we are not really close to 70% and 20%.
Would require.
Now, this is the case for only
Red Labs
a
based
single
higher
qubit.
experiment for this.
Now, if we have a combination of say 10 qubits, we have 2 to the power 10 different. So just for a single
Sort
qubit,
of
maybe
remotely
100
related
shots
to
of
what
measurement
the
might
mission
not be
is.
enough. Then
We have
for
investors.
larger size, how do we decide? Because for now, I have already information that it should be 75%. So if I find that it is close to
No, that's for us,
70%,
it's
I
not,
would
of
say,
course.
but
Yeah,
if it is a system, I don't know the number. Now, how do I decide the number of shots it takes that in the go it is giving me the right probability?
Yeah, so there is no easy answer to that. There's a lot of things that influence the, there's a measurement noise. Going to get noise from the measurement level. So, you know, as
We have many
collaborations.
collaborations. Invested.
The more measurements you can do, the better, right? Because the more qubits you have, the more you're gonna have to
Can be close.
sample. Now, what thing I can say real quick is that that's the reason why the best quantum algorithms are the ones where you take a very small amount of data, put into the computer, it does some massive computation on that data, and then on the output, you get a very small amount of data output. So like, because then you don't, then, you know, if I only have to do like a single bit, you know,
basically plugging in
sampling at
battery.
the end, okay, that's why things like classification problems might be good, because in the end, I might just need a 0 or 1. Actually, yes, I think.
Yeah, they have
But I think we can fit you over here. So, if you want to set the Are you, so actually, maybe, do you know how what's going on right now?
Yeah, I know what it's not done stars.
Okay, yeah, so this is the physics group, that's material chemistry, and then that's bio, and that's.
They need to also the modeling and
Okay,
everything
alright.
that comes them. And on top of that, you need to make them.
Go ahead and take that.
That quantum computing will actually help them like that. That's a two-stage thing which helps them make everything. So so, but yeah, let's say.
So the sampling issue is a problem right now. Because every algorithm you're going to run is going to require you to do a lot of sampling because you're doing, especially if you're doing things like amplitude encoding.
The models say, okay, so.
Yeah, if you have access to that.
Yeah, effective cost savings.
Yeah. Right, because you did like model reactions to
I think it's a measurement that's possible.
the products you get, or like the energy barriers to all your products and then.
Yeah, no, so how this works.
Give that numbers or exact probability, you have to.
Right, but I mean, it's not like, it's not like if you have an qubit, or it's not like the number of shots can increase exponentially, so like,
molecule candidates.
I mean, it will, if you go from, if you're trying to compare 1 qubit to a million qubits, sampling obviously would be a huge, but you can run 20 qubit simulations or 20 qubit computations.
So then you start with this
with
kind of
8 to 10,000 shots.
where you first
Like it's not like, it's not so bad that you need a million shots for 10 qubits.
What's the method where?
Especially if you know what you're looking for, right? You kind of see how it's working.
Ones which are left, they get smaller and smaller.
Part of it too is saying, given this constrained resource that I have, right? If I only have 10,000.
And then what you check there is then of course.
What is the probability of getting my correct answer, right? That's part of it too. It's like, it's part of the problem that you can just.
There are a lot of,
sort of constrain.
They're very, very successful.
Say even, say we have number of variables of 10,000. Then 10,000.
There are lots of different approaches to genome because 10,000 different startups. There's a startup that has to make it.
No, so
right, but right now you're not running a 10,000 simulation problem, right?
Which is like even if we take tens of people, it gives me 2 to the power 10 if the advanced applied.
Right, but you don't need to, but the point is you build an algorithm, building an algorithm that very particularly should amplify the states that you're looking for, right?
So they make
So
cuts. For example.
you're not looking just for any state, right? If you build the algorithm correctly, then it should.
But you can also rarely calculate a protein.
So,
As a matter of fact.
if the probability of finding that solution ideally is 75%, then if you run that heat isn't saying 100 times, like, and you get 75 or around 75.
Sí, voy a decir. Guys, you wanna get food? Is it getting cold? No, but they're gonna close up at 12:45, 12:45 or 1, so you may wanna grab food.
We're making him nervous.
Well, number one, the page. So it was a bit like, let's say, quantum computing at some point became this like super quickly expanding field, and the whole product is ADF, essentially T program, and then at some point, quantum computing mainly becomes very relevant for this, and so let's start to look into this.
You said your third year? You should about doing this stuff for real, because we can protect them for
Exactly, so
real.
that's how I'm
Yeah.
like consider.
I'm serious, serious.
Oh, what is like a scale?
I guess your background is in like theoretical qubit stuff. What, do you have ideas for applications then on what you would, how does that translate?
That's a very good question. So, I just started at Johns Hopkins like last week. Still don't really even know what my new projects are. I just know, hey, I should probably be into this thing. Don't, just from my own background. I'm still trying to figure out exactly what my projects and goals are. They're kind of like, hey, meeting people, figuring out things in the lab, meeting who I'm going to be working with. So, I don't think I'm really starting much on the application of, hey, we're stuck at a bottleneck or something. I think it's more like, where are we with quantum computing? And what benchmarks are we hitting? What are the different companies involved? What are the advantages, disadvantages of different qubits? And kind of getting more a general idea of the field. I think eventually there are problems that are like, hey, what can we do with certain quantum algorithms that could be helpful now? But I don't think I'm at least at that point in that.
Yeah, but
Do you have an idea of what you would want to try to like just
That's
in the dark?
right, that's a very good question.
industry that
Some of the things in my own sector look at things applying to like cybersecurity. Not necessarily cryptography, though we do have groups looking at that. Some people are looking even at like semantic taxonomy, like going online, looking at how certain languages connected that are kind of assessment.
Yeah, so then,
That's possibly something
then I
that could
would
be
advise
applied
you very much
in
to
the, not the near future, but kind of something that, hey, once we have an algorithm and a system and a problem, if there's this too many variables, what can we do to reduce that and get into like a working, something where, yeah, there's a handful of steps we can plug into a plan. Not again, the whole thing, that's just way too much information, but certain steps could be optimized, I'm sure.
Paper would of course greatly help, as you can imagine, and that field.
Ideally, so I'm curious, vision machine learning. So what problems do you have with
So you're starting here.
Yeah.
Why don't you call it, you're using these kind of getting interesting problems.
It would be a nice
working that, but then before this I was working.
Anything which is like,
So.
let's say is close.
Yeah, I'll
enough
put
to
this
the-
out. This might be like a really
Yeah,
basic
it's
way of
quantum, so
thinking about it,
what-
because I'm completely new to quantum zero. So what my intuitive understanding is, why can't I replicate the quantum computing gates and stuff? So the qubit can have like a superposition, so what's stopping me from basically giving classical bits of random assigning 0, 1, such that I don't know what it is, but then it's like a probability, call that my superposition.
It's a bit, let's say.
So I don't know what it is unless I measure the value. And we did the example where we were checking like which coin out of 8 coins had a head. So what's stopping me from assigning this to the GPU and then checking all 8 of them parallelly with like 8 different threads?
So I imagine.
Yeah, so are you talking about just trying to emulate quantum mechanical distributions? Are you talking about that you want to be able to create random distributions that have, that mimic what you get from the
We had a theory talk yesterday. It's a theory talk yesterday.
No, I'm trying to think of directly taking all the concepts that I'm learning over here, called and then directly applying them using GPUs and see what exactly is different that makes quantum computing.
Well, I mean, you're exploiting quantum mechanical effects, right? So superposition and entanglement are not things that you can simulate, right? But you're simulating say quantum mechanical, and you can't
So
that
there's
sort of simulation of
Oh, you want
the
to keep
probability
the,
is not the same.
that I came across
Actually
recently.
harnessing
So,
that
like, here.
Right, so the reason why quantum computing, works in principle, right, is that, you're harnessing the behavior that this phenomenon of
Essentially,
in a way that allows you to more efficiently explore spaces of the problem and in different ways. And being very general here because it depends on the problem you're trying to solve. In terms of optimization, for example, which may be relevant to some it's this superposition feature
It could be
and
anything.
the entanglement that you entangle things together that gives you sort of a non-locality across space, which is searching. And you can use basically interference created by this entanglement and by the superposition. You can use all of this together as a way of sort of searching a space, right? Searching a space of solutions. And what you basically do is you devise quantum algorithms. They actually cause constructive interference towards solution states that correspond to your and destructive interference towards those states that are not part of the problem. And so it's this ability to create this non-locality and this sort of constructive and destructive interference that give you the ability to find, for example, optimization problem, solutions to optimization problems faster. Now there's a lot of subtlety here because there are heuristics, there are things that make about problems that make you bring me closer, and there might be cases where you say, I know enough about my problem such that if I solve it classically, it's always going to be as good as solving it on quantum computing. Why do I need it? Right, but it's always about finding the right problem,
And of course,
where you don't have enough of a bottleneck, and sufficiently, I guess say insufficient information about the problem such that you can say, classically, there's nothing that I can do with some complication, nothing I can do to make this problem easier to solve. And that's when, it may be possible that a quantum computer
For us, it's Okay, so coming back to machine learning. So I was having a discussion with Thomas yesterday, where I'm working on a project where I'm having building a graph based on a user prompt on LLM and then trying to find out sensitive data from that. So I'm doing this via a local diffusion approach, but then he was telling me about how computing is directly applicable to this because quantum computing mostly only looks at global approaches for the entire graph rather than local approaches. So that could be one of the computational problems maybe for quantum computing.
Yeah.
This is a quantum
So what you're saying is, you say global solutions. In this context.
Okay, so I'll explain a bit more about the project. So I'm making like tokenizing the user prompt.
Sorry,
I'm tokenizing the user prompt.
okay, I'm not sure I know what that means.
Okay, so basically, I as a user, I'm chatting with an LLM.
What are you?
And then I give it a prompt with multiple words, including sensitive information. I'm separating each word or like parts of the sentences as a token. And then these become my graph.
We don't know.
So these are my graph segments right now. And then I'm tokenizing this tokenization. After this, I'm doing diffusion, where I have like hotspots which I identify as potential sensitive data. So the way that the graph is built is such that
to make along the way. I alluded to this sort
of. Do you guys know what attention mechanism works in transformers?
But there's also different point operators you can use that give results.
So basically you have a graph and then
where are on the graph.
Highly correlated words in the English sentences connected by edges.
Weird from a classical perspective.
So they say, I am a boy.
Doesn't matter where you start, right? As long as your graph is
Correlated to I because it's talking about me.
say, well,
There'll be an edge between these two. So I am a boy, 4 words. These would be like 4 different nodes in the graph.
We did multiple
And then deep connection between boy and man.
setups.
So that's like the high level way to put it.
Especially when like,
In this,
even
I
the speed of
sort
the
of
chasing.
give like hotspots,
That
or like
quadratic speed,
confidence
I
levels,
think it's all
and see
present
which
in
one
some
could
classes.
potentially be a sensitive
I mean, you can
data.
imagine very
And
much
then
that like.
I do something called graph diffusion,
You know.
which is basically
So
aggregating the
maybe-
nodes with respect to
maybe
its
like-
neighbors.
You can imagine
So,
degenerate
when you
types
do
of
this,
graphs
the
where
sensitive
it would be
hotspots
hard to spread out and
diffuse throughout the network and then give me
so then
potential,
it
more
becomes like
potential
your
sensitivity.
graph one
So
that plays
this is
nicely,
something
right?
that's
And it's hard to
local because
answer
you're looking at
essentially
your
asking
closest neighbors and doing
questions.
it. My talk with Tom was
You can
giving
talk
this
about, for example,
intuition
you know,
that
is your
this would
matrix
not exactly
acting
be
product of these
possible
parts,
in a
right?
quantum
And you can measure how many
computer
integers that are
because
zero or not.
quantum
That's just
computer
gonna
looks
be
at the graph as a whole, not
you
like
know,
a
my
node.
100 by 100 matrix has, you know,
Yeah,
200
100%.
non-zero entries. Is
I
that
don't
sparse?
know, right? So
Yeah,
the,
I
I mean, I haven't
between those.
tried using any sort of graph neural networks in this context, or thought about transformers on the quantum computer. Most of the things that I've done are more of like classification problems, which are like, I like the kindergarten level on machine learning is the same here, right? So, I'm not sure. This is, it's an interesting problem.
I need to kind of go back to the
Maybe there's more, maybe actually you can also ask, I don't know if Mark had any insights at all. Sorry, doing things with like transformers on, you know, like machine learning, right? And transformers on quantum computers. Do you know anything about like how this, you know, anything people have done or?
I don't. I don't know what it's talking about.
To actually do different genes, simulate and see.
Yeah, that's a challenging one. How have you maybe I guess maybe this idea only came up for sort of the connection workshop. Have you tried sort of, you know, doing literature searches to see if any? Okay.
This just came up yesterday.
I see. Okay.
And I didn't have the opportunity. I give it to them. I probably do it over the weekend and then out. One is see what's up with what exactly the problems are. When I'm along that approach and see what exactly is stopping me. And then go dive deeper.
Can't look at specific parts of the version.
Yeah.
Okay, I don't have a whole understanding of it myself because I come from quantum computing side, but then what Thomas told me and what I understood, I look at the graph as one singular entity and not like within the graph as node level entities.
You have to figure out.
Yeah, I don't know how this works. I mean, usually, like if you're doing quantum machine learning, usually what you do is there's
Basically a version of a
layers of the network now are basically objects of the gates. And these gates have tunable parameters. And you can, much like you have in a graph, you have nodes that you have to, you know, to sort of determine the weights of the weights of the nodes, the weights of the edges in order to like learn, right, learn the data. And so usually what you're doing in a quantum neural network is you have layers of parameterized gates. You're really trying to just learn what those angle
I know that
parameters should be.
quantum approach.
And that's usually the way they,
Yeah.
you know, but each gate
There's
itself
the HHLs.
is a node.
I know that there's
So
some,
I-
they mentioned in that book.
You know,
There are
and
some
if you want to
ways-
create
I mean,
active
weight
I'll
updating.
say each gate is a node, and then each kind of qubit is sort of like has multiple layers attached to it.
Oh, so you're saying that.
Where so if you
Quantum
want to
are
get interaction
kind of
between
almost doing
nodes,
the like
it's kind of
traditional
an operation.
classical machine learning.
So usually what people do is they have like some layer parameterized weights, and then they choose maybe they do
I wonder if there's some
cascading
version
CNOTs and say, okay, interact with them together, you should repeat this multiple times.
You
then
sort of
sort
learn the weights
parameterized layers
of
are the
you
ones
start with
that
like a
you
complete
break.
graph, all the weights being one,
And so
and then you slowly update it.
yeah, I guess I'm unsure why you can't
Right?
do what you're talking about here is treat the layers of the gates as sort of a representation of how the gates should be structured. So for example, if you have an edge between two nodes on the graph, why can't you say, okay, that means I need to tune the gate here? And then, another case, I don't have a prohibit gate because
I did find
those
a,
edges are not
uh,
connected. I don't know if you can kind of play.
I
this
did
game.
find a math paper on the probably like string reconstruction of substrate
Like I said, I'm not
composition.
sure myself, but then it could possibly be the.
Yeah, the cloud
And it's
service.
specifically talking about.
When you work with
mass
like really
spectrometry.
complicated graphs, it's not just gonna be enough.
And
to get
it's-
two cubic gates.
Too close.
You're gonna have
Even
like
since there's
one
a giant
couple
string you don't know,
high-dimensional
and
difference.
you have a bunch of
Level
overlapping
connections.
substrings of
Yeah,
the string.
Right, but it's still
Reconstruct
a graph, right? It's still a graph with a set of nodes, and you just have more nodes, more edges between nodes.
Yes.
So, if I have multiple nodes going to the same, or multiple edges going to the same node, I'm just.
Sorry, in the sense,
I'm kind of
using the on the transients of
At
multi-dimensional
least in
blocks,
this, my very
by
naive
reconstruction out
way of thinking about how to
demonstrates this out at the size greater than or equal to 4.
That just
From
makes
their
sense. I have to
subgroup
look into it,
of near
I'm
quadratic.
wondering actually what the product
There's a lot of
is.
things in that.
Myself.
So-
You don't even give all the idea.
I wonder why they care about things.
Going on. Quantum neural networks.
But I'm sure you have to have.
They are orange. People are applying such.
What if it's quadratic time it goes like? Prime group.
Yeah, I mean, this is what people typically do.
I don't know, that seems to be kind of the typical.
Oh, yeah.
Speed up for so many things, like.
Classification, there's been some, like feature.
Maybe that's just
feature
because
learning,
if you come up with something that makes it,
dimensionality reduction type problem.
about 2/3 in the exo,
There's,
just might as well. be
there have been,
right, any kind of certain
there's
problem.
been some work in,
I like students,
Yeah.
I like,
reservoir computing, which is basically you're trying to learn sort of like stochastic signals or like some signal over time. You're trying to get like sort of time data.
I also.
They've done this on small sets. There's
What are actual
there
problems?
is quantum reinforcement learning, and people have done this on like 2 or 3. And so you're basically trying to move forward in time and optimize the path or something.
Could you, does it work in similar way, like possibly randomly put some workers and finally the output, it shows a higher reward, then you go back and try to optimize
This is
that
quadratic
so that-
speed now, is it?
and by the process of optimizing, we keep changing the workers.
It's good.
So, yeah, I mean, it's very much like a neural network also, right?
What are the operations? They take it. Because if it takes polynomial time,
If the.
the problem is if I have to spend any time
So
being in my
each
interest and
node
any time
has
reading
something
something,
that's like
I don't care if I'm going to
So
is
they're
sub
talking
n time,
to-
because I have to
talk about
in on the internet.
like Hadamard gates, which basically takes you from like a 0 to the digital state. But there are gates that can take you part of the way, and maybe when you have a 75% 0, 20% 1, and you can or anything, right? And so that becomes basically you tune that, you tune those gates like that, so you partially rotate qubits at each layer. And that becomes the way that you train.
You should elaborate.
Kind of tuning the rotation in the block scale.
Exactly, yeah.
Camper.
And then you harness entanglement by
Oh,
applying some of the entanglement gates.
Because I've got this.
How you choose the gates that you pretend to use, like, what,
It usually does.
should I entangle everything? Should I not entangle here's the how should be all, right? It's very much like
Cryptography falls
like
apart,
just so I get
right? And you solve that and hold it on time. You have bigger
you build some intuition, and
Right.
then you're the only one that knows how to train these things.
Actually,
Like,
only
that's
right now.
kind of the way it works.
Microscopes, so
But a lot of people, what they're doing is
Question
they're
then
taking a
So
large
it's like
problem,
monolayer,
and
I've
they'll
tried
go
a
like
lot of
layers
different
of
things and I
like
found
puzzles
it.
they'll start to like
Yeah,
carry
right.
on.
Yeah, and also
Right,
take the
right,
approach
factoring
like
is
with
interesting,
the
it's on there.
polymer, sort of like the same idea.
Yeah,
So
so
you
have
take
layers
the
of
polymer
bit,
as if it were
but it's
cake,
trying to
and then
learn
you
to
try to
look
like that and get it to like,
complex features.
you know,
that
form
usually
different
have
layers.
that.
But the
So
coordination
put that there and then
polymer
they'll
I'm
like
working
span
with
back out.
is
to a
not
possible
too
network.
deep.
Like, I'm glad you asked.
So the interaction
It's like an autoencoder.
layers
thing.
are
Same
not
thing.
direct.
No, it's kind of like almost
They're
philosophical
like
question,
high
because like the
five
blunt
back
answer
And that's
is
kind of
like the
because
linkers.
you can't encode.
So it's kind of
then
like
you
a
probably
stronger
solve the
interaction,
faster.
it's not
Is it kind of high?
the
get
useful
slightly more
way
philosophical,
that you would
also use
exfoliate, right? Because when you
Sudoku.
exfoliate, pretty materials.
Solving a
are
Sudoku.
Yeah,
not
like you
like
just
N by
train,
N Sudoku.
you're just
So
taking
it's
extra neural
proven
network
to
on
a lot
specifically
harder
determine
than
whether
we
it's
thought it
You're
would
looking
be.
for the
Why
output
is that?
and
And
classification
And
is
so right now,
structure
it's
is
like
this
focusing
rich
on the
enough.
You
proof
know,
of
you can try
concept.
to
Code
maximize
logical
Like
the
the
probability of
on top of
Right, you can
the
code and an ordinance.
and looking at
If
what,
I,
you know,
now you're
gave you
now you're
an
up.
what
argument,
interesting
certain
data I
extent,
might
would
get
convert it
from
for the
the
class.
wrong
That's all,
one,
and also
or
a quantum
the
leap problem,
lessons.
and the point is that
And
Sudoku is a,
then once I prove that
has enough
concept,
stuff in
then go
where
back and
you
try to
can
actually
encode
solve
every
it.
stuff.
and so factoring is not gonna be complete because it lacks that
In
structure.
a more common language, basically, in Sudoku.
You know, you can do everything, you can do all possible, but you're just gonna now be limited.
No, because like,
you have, the more tries you have to make.
okay, so we are
Yeah, there's
also
been a lot of
doing,
work
like,
on
one of
trying to
my
better
colleagues
embed,
is trying to get that to work.
Because, you know, you
So
don't-
my
yeah,
experiments when I
it is
started my
like coding where you basically
were
say,
kind of doing
and
some
specifically,
technical
like, all those
precision
boxes can be
binary
related
and like
to each
getting
other
both the
via
measure
kind of complicated
and
logic
data
and, you know, then I.
in a way that
I,
like
the
factoring
sublime
isn't,
go into
because there are bits of a number
React,
related to
and
each
then
other,
whatever
whatever
amount of
use
bits
it.
I need is.
regular
But I
way.
did very
But that's kind of
different
like,
experiments in
in
that
code
was like
complexity
really
when you
working.
want like
Because
kind of
the
way
polymer
use
was
it.
not
Right,
getting into
because
a
whereas
reactive
in, like,
state
Sudoku,
where we want to
you can
bond with
set
the
up these
metal.
complicated things like
And
this
so
has to
like
be
that
three,
never
because
worked.
otherwise
But
this
one
thing
of my
could be
colleagues
three,
is
this would have to
working
be
with,
the lot
like,
of thing, and that could be
a
arbitrary
cluster
long
that's
nonsense.
already
So
you know,
that
like
must have the
bond
same-
it
because
and
of
trying
that,
to
must have
get
the same
abstract algebra, like.
sort of like a
basically
ligand
like,
exchange
uh,
reaction to happen in
like
this
a, like a
furnace.
theory, basically, to
But
better
they've also been like having a
symmetry
very hard
present.
time. So
and-
just
and try
figuring
to
out how to
efficient
get
coding
these
schemes.
to
So you're, like,
grow in the
actually
gas
using,
phase
yeah.
is
The way that you
very
apparently
apparent.
track
And ideally,
Right.
if we get that to work,
And even then,
then
right,
growing
factoring
monolayer would be easy.
Otherwise,
But since we haven't gotten that to
general
work,
number of fields
then
spending
like the
all your
other
time
way to
trying
do
to
it is
code it.
It's not one
visualization,
time,
and
it's
that's
not two, yeah, it's
And
not
like
like four,
lose out on any
it's
potential.
a really complicated runtime that someone spent the whole time.
Yes, both at the same time, see which one works faster.
If you improve the phase, then
If you have a
with
product
the
that's
state,
complex.
then single qubit can have infinite number.
So my rough understanding is there are intelligent ways of very significantly cutting down the search space. So you're still doing some amount of sort of force, but instead of thinking, if I remember correctly, yeah, but when you can measure,
You can measure relative phase.
so you are applying
What matters in quantum
a
mechanics is relative
cut down of
phase.
that search space by using clever number theory.
And you can get that information just by changing your basics of.
Like there's a little bit of pre-processing,
Think
and then
of that,
also
like,
searching.
imagine like, you know, I'm in a dark room,
Certain
I have a
numbers
sphere,
you
I
think
have
are
a
like,
ball.
and actually this is how Shor's works. So if you look at Shor's algorithm,
And
there's
what
a
I tell you is
pre-processing
that
step where you
like, you can
convert it
only
into a
look,
different
you know,
problem,
I give you a
it makes the
flashlight,
search
I
space
look
smaller,
at
it
the
makes the problem you're trying to solve
from,
easier.
like,
And
the
the
top
difference with
to the
Shor's
bottom.
is eventually you
That's
get to
it.
this period line that's all the inputs part classically,
So,
and
you know,
Shor's just
it has all the interesting information is
you
around,
eventually recover your rate of
around
solution,
these
but it's
sort
like
of
3 or
later
4
ones
steps
that
long.
fall, right?
So
The way that you get to the information is basically by rotating
Of the numbers.
So that's what you can solve quantum computers by applying various gates. You can
So put a simple
rotate
explanation
in different ways. Even though your measurement is restricted to those two axes, you can still rotate and get information about the other.
So does it mean we can train it as a single qubit or
Yeah,
it's
like, it's a really good question, why isn't factoring complete, or more generally, like, what is it that makes a thing,
would be 30%.
why is it that so many things need brute force and just some don't? There's not, I'm not aware of 16, it's a deep mathematical question.
Having that phase.
Also,
So a single qubit
in fairness, the
Yeah, so that's what they do. They say like,
non-existence
imagine I
of quantum
choose
is an
a
algorithm
phase
for
and I can
problem
choose like
is a
6 phases
hypothesis.
that you could have.
Like, we don't actually know that, right?
I don't want them to be too close
It could be
together.
that actually there is no difference.
I want a
So it's
million
possible,
phases.
right?
Like, but all
It's
that
possible.
because
One
now you're gonna have
potential
like sampling
explanation
issue,
for
right?
what
How can I
happens
tell
to
the
different
difference?
problems is
You know,
there is no
too close.
difference.
So you have to choose
Right?
that
Like
sufficiently
that's
close.
so there could be a
And
linear
then
time
you can take,
algorithm
like,
for all
one
of these
cube, like,
things.
a certain amount of information embedded into one qubit. Maybe there's like 6 bits of
Yeah, factoring is
information.
easy.
Embedded into one.
And there aren't that many problems.
Taking advantage of
This
different.
is something that like
mainly
about quantum computing, even if all of our best quantum dreams come true, and we get exponential speed ups on everything we can imagine.
The better your
Would
computer
be-
is, the more phase you
We
may
are not very well, because a lot of crypto problems are also in that intermediate, right? Which like all the
What defines better, like noise, the amount
are,
of
a lot of them,
bits?
lattice cryptography, which is things like
most
short
short
spectrum
spectrum
problems, familiar,
measurement Right,
like
like,
a bunch of
you know, for
vectors.
example, they were saying here that,
Basis, what's the
and
shortest vector I can make?
oh, you only need a
integer
thousand
combination of
thousand
vectors,
vectors, right? You know,
That
versus-
is an superconducting intermediate
but it's
problem.
already cost.
I don't quite
Right, not
understand that
inconvenience.
because, you know, superconducting qubits, surely you have
We,
a lot of.
we know how to check it in the
that
sense
even
of,
if,
if your first question is, can I make a vector short?
like, decoherence effects, like.
We know how to check that because I can hang that
So every day of all that is things. So measurement
But
process.
yes, like that is a target quantum computing.
Realistic,
It's feasible
when you know, like.
And then
They hope not,
That is like.
there goes all the NIST post quantum standards, we have to do another round of it.
Connects, you know, like a metaphorical spring here that connects to your qubits, and you have to basically jiggle that string and get some information on like what state you're in.
Oh, sphinxes?
And
So
back
math
then-
release is based on,
So.
yeah.
So meaning of these springs together.
I wanna say
springs
math
sometimes
release is
talk
based on the
about-
knapsack
and
problem.
So you have to, as you increase the number of qubits you have, you now have to make sure correlated measurements across them, even if one
Yeah,
thing.
well,
And you can have classical,
you know,
you're converting signals from superconducting qubits from down at
broken
millikelvin temperatures out to room temperature, it has to be
Okay.
layers.
There- there-
So that's what I like.
Electronics, all this other electronic noise, and so in the end, it's, you know, there's always some probability of getting caught in this.
And then also to your other
These systems are done.
Sphinx or.
I think Sphinx did get selected.
Right.
I know, I don't.
These systems have the same
To
issue.
your point on that, a lot of
Yeah,
systems
technology
don't have a reasonable assumption on it. For example,
I'm not quite
AES.
sure.
Yes, I know.
It's just
Based
AES.
off of just like.
We're shuffling things around. I don't know.
And they decide.
He was saying there's less
Yeah.
fields in there.
Yeah.
You're kind of
So
shuttling
I
them around
think-
rather than transferring
I
it
think
so
Sphinx is
far,
like-
but yeah, I don't get the measurements.
Yeah.
Exactly, yeah.
I mean, you with, so the big problem for travel typically is that when you measure,
I just walked
in
in
travel, you
back
measure everything at once. So that's why shuttling is so important. You have to shuttle, pull things apart, measure the qubits you want, and then shuttle this off, and then, so you only want to measure. So shuttling is very complicated, so I don't understand exactly
So that is a reasonable abstract.
how they define it as, you know, it's shuttle in a way that they can measure subsets of qubits, and then.
If I hand you a slide, can I ask you, is this
When you say costly, you mean costly in
The
terms of
answer is
noise?
yes, I can prove it very quickly by solving this.
Yeah, 'cause I mean, you're basically
The answer is no.
traps.
How would you?
So they're like simultaneous.
If I tell you this Sudoku is
console
unsolved,
helling the
how
qubits in
would
one
you,
direction.
how could I
traps
possibly
in
do
another,
that?
and they kind of switch
Other
around.
than sitting there and
So they like move them,
Just take
have
that
to like, basically like.
So this is
keep
going
that
to be any
magnetic field going,
question,
also like
answer,
another
we
magnetic
can
field
check
also
yes
in
instance
one direction. And so,
Oh,
you know, that's a very complicated process. With
And then
And
question
magnetic
is,
fields
if
take
you
off.
just negate it,
It's like, there's just no way around it.
factoring
so-
is confused because it's in both. The question is, does this number have a prime factor within its range, right? Some equivalent.
So the machine learning.
Regardless of who answers yes or no, answer, it can use
Worth
prime
looking
factor.
into.
You can check
See
if
if
there's
there's
a constant
there.
number.
There's,
And
what I'll say
whether or
is that
not
the
the
quantum
answer is
machine learning
prime
field
factor
is,
Yeah,
is rapidly changing. And our understanding of what we can do, why, or whether or not we should even consider is a rapidly evolving.
Yep.
Based on that, how to calculation and
Idea
the spectrum
debate.
energy levels.
But it's
It's easy to
nonetheless
check, as in if I've solved it, I want to prove to you that I know the answer, because I can hand you the prime factorization.
We still see a
So if
lot
you
of
say
that
yes,
stuff.
you can just give me.
Oh,
So
factors.
I
Yep.
think you should talk.
And you say
Because
no.
the.
I also hand you the prime
like,
factorization, and I said, see, look, none of them are in that range yet. And you can check that the prime factorization again is valid.
Okay, yes.
Multiplies here and alone.
Directly.
I get, what he kind of told me was,
So
it
any-
was a hot topic until maybe 2018, 19 or something, when somebody set out to show a lot of
And you can do
the
that.
quantum machine learning algorithms quickly outperform.
Yeah,
the
primality
classical.
testing in
And so the
2006
topic
was de-randomized.
kind of,
But yeah.
I would say got
that's
completely
one of-
debunked, but a lot of.
But, which is really funny, because it means,
I don't
if I
know
have a number and you ask, is it prime? I can say no
And he
very
probably
quickly.
knows
You say,
that.
great, what are the prime factors? And then I take a very long time to get back
I
to
had a similar question
right?
about quantum
And
machine learning,
this
because I know a
register
little
here,
bit about
because
machine
anyways,
learning, but I
computer
didn't
science is
understand what the quantum
Yes,
part
NP
with
code,
adding
they're
on, like, there's
separate
some advantage,
But if
I'm sure,
factoring
but
for NP
yeah.
because it's
Not
also
point to
so
talk about it.
it can always be completely combined with all possible
combinations
right?
zeros and ones.
Yeah, I mean, the big-
Because
big
you can
thing
take any
is
NP
it's
problem,
always
you can
believed
turn it into
that-
factoring, and then because
you
you
had
had
quantum
factoring
data,
isn't going to be.
that's
And
where
you
quantum
also
computing
by,
machine
yeah,
learning
that's
would be.
zeros.
So that's kind of an argument.
The
It
data
doesn't
is inherently
really,
quantum.
it explains why correlations don't
simulations,
work.
it's inherently quantum.
It doesn't really tell you anything about the structure of the problem.
But it turns out that
Other than that,
there are certain sets or types of quantum data that you can just easily classify.
value of that
Just
which
classify.
corresponds
So then, okay, well, what's
Does anyone want any more seconds, thirds, fourths, fifths? Are we all set with lunch? You're gonna start to wrap up, so if you want something, grab it now. Okay?
sometimes I do think I should do a
Yeah, so it's
like
the,
giving it practice on all the things I talked about.
I guess it brings the question of like, what is specific, what needs to be specific on
Yeah.
data in general. Tell me whether or not I should be using it one way or another. This, and that's a challenging problem.
Dependent on
Summarize. There is some actually after looked at power of quantum data, basically. Like, what is the amount of information?
That's how the way it is very, actually, maybe it's not.
There are cases
I'm saying until then, primality testing was not in deterministic quantum. There were randomized methods that would tell you if the number was prime with height 70. It did not have a way of like definitively determining
the best result on average.
It
could be that quantum classical say, which one gives me the best result overall, or like the best result, like sort of like
Because otherwise, I mean,
max out of
I
all
give you a
the
fry.
testing data I have.
I
I'm
saying.
But
yeah,
does that matter? I mean, it's like, if it's like really good at classifying this particular element, like does that actually matter, right? Probably the average is more important.
Yeah.
So
Right.
that's,
Yeah,
that's
saying in the most simple thing.
This number.
I'm still unsure where it's going, where this should be.
without prime DP, just
And then I
set
give you
factoring.
the two primes.
The same with George
Leave
Wayne,
it so
it
much
is-
data, like
Ah,
how many,
and
if
so,
a node is,
So
I
there's
guess one of
there's
your
a question
questions.
about one of the stack exchanges.
Is the number of qubits gonna be
There
the number
were
of
existing
layers?
primality certificates. So there are mathematical ways to be this prime with extra things. Right, so I could hand you those, it would still didn't go into the
Yeah, that's why I wanted
Nowadays, you
to-
don't need the certificates, you can just check your prime, I don't need that for you. But before then, if the person proving it to you, not only would send you factorization, but also proof that these primality certificates and attach to each of them as a factorization, say these numbers.
Along the same lines of how exactly the environment.
There are like, as in, there are additional numbers you can provide along with the number, such that there's a routine calculation you can do with those extra numbers, such that that calculation will only work on the numbers. And those extra numbers are hard to find and are tailored to the understanding thing, but it's a certificate.
Oh, that's kind of cool.
Yeah.
Yeah, I mean, you still, it depends on where your access data comes from.
Wow.
Yeah, what is, how is prime?
Yeah.
I remember 25 being a top, I just don't know if it was.
Because she's like,
I don't remember.
So the,
So she doesn't
the excited
choose
state,
which one.
all the states.
The AKS primality test.
For the range.
Oh.
To, when you compare these in the register, you. So you, yeah, do some kind of.
In many different areas.
This is explained the components of.
This happened a couple days ago at work. We had one of these breakout sessions talking about quantum mechanics.
Of which I was told to read and I was like, well, I gotta.
Right, and so there's Roxy, no,
Oh.
Roxy.
Let's say that,
And we're sitting around and,
Uh,
Roxy goes.
Or you can like.
Right, so suddenly it's not
deal
just
with
Roxy, it's Roxy and I. And then finally, gets
certain
the
amount
like,
of
all right,
time,
who's
then-
leading this thing? And Roxy
Right.
points at me.
Because somebody.
That's all delegation.
That's right, delegation, unilateral delegation.
Is there?
You've all been told.
I would want to do this, even if it doesn't necessarily solve.
I should have put it at someone
Yeah.
else, I could have kept it else, yeah, that's my
Yeah, you
fault.
would.
I wouldn't, and that's why she wanted it, she knew that I wouldn't put it anyone else.
I think we probably spent most of the time trying to figure
Yeah, you
out
need
how
to
to
come
input
up
and
with
map
what
it
you
before
need
it
to
did anything
Okay,
useful.
cool.
Those seem to be like the big things I'd be like, all right, let's try, oh, how do I do this? And like spend the whole week researching all of that or something like that. Exactly, yeah, so that seems to be maybe more of a bottleneck than the actual software, again, seeing kind of the process, it seems fine, but I feel like getting to that part could be worse.
Right, so
NP interview.
I guess let's like, so like, so what, you know, what would be the problem? Like,
Well, so that would be.
what would be the problem that you would say, hey, I
That would
want
be
to
the
test
class.
this out?
Can I get your?
May not be the problem at the end that I really
So,
want to solve,
what-
but I would want to run. I would want to run.
So what you
let's say,
said was
safe
the definition of NP intersected to NP, right?
Yeah, maybe it's a
That class
problem,
is
maybe it's
a subset of NP
And
intermediate.
calculate
There are also
classes.
problems that are not in co-NP, that are one or the other, but just aren't.
No, we can collaborate.
Nuclear
So another.
physics, like a big problem for us, is like the uncertainty in the nuclear matrix elements, like if you have like a
So if I have to graph.
dark matter particle or
exactly
something
equivalent.
hitting
So not
one
edit
of your
distance,
detectors.
as soon as you generate edit distance.
There's gonna be some uncertainty into that because we don't actually know what the
Two
energy
graphs, are they the
levels
same
look
graphs?
like
So
of
labels
these
will
heavy
be-
atoms.
That's
So it would be cool if we
NP.
could get a more precise estimate on how the actual electrons or gluons in your heavy atom talk to each
Or at
other.
least
I
determine
don't know
whether.
if that, it seems
from
more
there
like
you
with the
can-
molecular, like,
Yeah.
oh, I
So
forgot the name.
that-
Okay, like quantum, in quantum, the last,
again,
in
if you
quantum,
have a
yeah,
thing
it
that
sounds
tells you
like
what
something
information
more on
exists,
what
you
that
can
would
turn
be.
that
So I think that would be
into
cool,
a thing that gives
but
you-
I agree.
Roxy asked about this and I.
For me, the logic was
I
probably
had to do some digging.
a hard hurdle.
Sure.
But that's NP.
I
It's
agree,
in-
that's, I mean,
It's not
that's
quite in
the
co-NP.
main
It's in-
problem, I
I
think,
think
for everyone that is.
it's in the
trying to get
randomized
application
version
done,
of co-NP.
not to the
So
hard.
that is to say,
But if
if the
it's
answer
more
is
of
no,
a, it's more of
someone
a, you
can
know, I guess,
prove it to
just
you
kind of thinking about like,
randomly with some
you know,
chance.
if you had,
They have like
if you
some
had
resources
odds
for
immediately, like, you know, what would
It's
be kind
weird.
of a.
I don't
maybe
understand.
something to look
Well,
at,
how would you
there
prove it to
is-
someone that you graph?
There's still gonna be things that you have to research.
Right, so like.
Or.
Is this the right problem? Should I be looking at this problem? You know,
Cycles that are
This is a crazy idea.
But generally,
But,
so apparently there's some
more of a,
clever
I guess,
random way that
saying
works
like
most
off the top of my head, I'm really interested in
Yeah, right.
how to simulate.
I don't
these
understand, I
models.
haven't looked into it.
I don't, you know, I wanna simulate.
So that's an example of the ones
Can I do that? How do I do that?
One where we
Sort of things that
Not
work.
detection, so how familiar are you with not?
It's more of a kind of
Not like KNOT.
I know that there are no mods.
I think about the thousands crores near the channel.
So if I hand you,
In the if we want to go there properly, then we have to go to like highly fine mesh. So that we can do with our classical computer, classical resources. So we always rely on modeling.
Two dimensions, you cannot pass.
If I get the opportunity of using hardware I will use finer mesh and then resolve it. Then I will try to compare that with our models. And we can, from there, we can even improve our model, because for the modeling we rely on different coefficients. Sometimes they are empirical, sometimes they are based on some experiments.
yeah, it's no matter if
Like,
you can always pull it in a new direction.
Exactly. By solving
For the mesh,
Wonder how much looking.
then you can kind of, with this
So
construction.
the question is, if I answer it not, is it really enough? Or like,
You can kind of wrap this, wrap the time of the receipt.
right, yes.
Certain components are more.
That's NP. Is it actually?
It's a good thing and a bad thing, right? There's a lot of people working on it.
It's
You take dividing by a small number.
What would be like connection between
Yeah, no, what you have
In a
is.
sense, what do you mean by that?
Well, the research reframe quantum computation as estimating the Jones polynomial of right, which is a certain knocking variance basically. So there are
Yeah, it's a very, very different map.
but there's some distinction between
So,
the very
So if you see this, for example,
But the real
yeah,
point is,
there's
I don't know
a-
what he's getting at. Like I understand
Size, mesh density of the
non-system.
So like,
checking whether the thing is unknot.
you have to decide whether this will go into discretization.
So I'm thinking of
Jump in if you've
operation,
got
like,
real
it's
world
all maps.
No, where's the last one? Like, instead of AJ's
Yeah, well, that's the
So
section.
No, that's
you have a
true.
different ways of getting optimization of time.
Okay, I understand.
Yes,
You
you
can
should
decide
spend
on
the
the
conversation.
next
Next time you find it.
Next time you find it.
Expert
Yes.
that's at least the.
But no, it's a
You have
short
to decide on the
Okay, so Europe,
So what you can do is like.
And so that resolution.
Again, a couple of crypto problems. Right?
So what sits in the post quantum?
And so you can figure out what some TX requirements and that.
If you got paragraphs or something, the state on it.
You map that. Based on the X, you get a certain number.
This is really the thing we do, so we'll- yeah.
Okay, yeah.
Basically, that's
I
what
was-
we
I
mapped
have to
onto.
say,
Which is-
What you then do is so the finer resolution you have.
I was
There's
thinking
not
basically, yes,
a
So that's the map. All of the other solving the different.
But they are putting all of their eggs in kind of one.
Yeah, it's not the best.
It's the,
So
yeah,
some of
the
these
translation
operations,
of problem
yeah,
down
laser
here,
mapping
which is
to-
non-trivial.
But you almost need to be in
But
a
it's
state of what
more or less.
the one that's.
Yeah, there's,
In liquid
I'm not
simulation,
super
the,
really on the
you have
exact
all-
reasoning, but there are arguments like that.
Second,
Like,
yeah,
if you wanted to be able to verify basically it works, and that's setting an intersection, and then you can't put that.
Easy to
Looks like
calculate.
Something like
in
that.
one direction.
There are details of that that I don't fully understand.
coefficients are
There's also
based on
generally
the
crypto systems, you need to be
chemistry and stuff.
Right,
That's
like
done
crypto,
above.
ciphertext.
Part of it.
I don't just want it to be that there are some ciphertexts that are
And then you have.
correct, but then most of them are.
Then you know.
But NP problems are almost never part of it. In fact, I'm not aware of any NP problem that is hard in
And
And it seems like
What is, what are they?
they're only hard in the worst case. So if I randomly
You get
generate
Hamiltonian.
problem, actually
Much very easy.
it's just that there are some that are.
Yeah, and we want.
No, that's.
And the reasoning for that might be that
That may have,
you know,
even
like
the
it's
interaction would be
really
really
as
as
complicated logical things.
That's
In order for it
the
to
like
express
I
that
think Kieran was talking about
complexity,
yesterday.
it kind of also has to have like a lot of dead space.
Freezing of the orbitals.
Like most of them have to be
Like
easy to allow you to build
molecules, and you say, I only care about the valence electrons, the bands.
So those are the internal-
Yeah, and then I throw out everything else, so then that Hamiltonian gets smaller, and more local.
That's on sparse.
So, no, it depends on, so, but 3 by 3 Sudoku is solvable in
To try to simulate that, basically,
Right,
turn that
you're gonna
into
go behind the
a scheme
But for a Sudoku, it's n by n. Yeah, that's an
Or you don't use.
No, it's not
Use another kind of
Like
like.
my point is
Right,
easy
say,
in.
series of.
Cascade.
Cascade.
Sure, yes.
What is their condition?
Yeah, that's.
Oh, I see what you're saying.
Yeah, like
That-
I feel like I'm
try to find
trying
maybe
to
around the same
Numbers you know,
optimizers.
because if there's three of them.
Optimize.
Always.
It's really easy, yeah.
If
So
the
very,
numbers,
very
the
different.
numbers you have inside,
Yeah.
how does that scale?
So, all that NP says is there exists some Sudokus as you make it bigger and bigger that take exponential time to solve. There are some Sudokus you have to predict. Are those Sudokus particularly sparse or really dense? It depends, like, I have to look at those constructions of those. You could write an algorithm to produce them and then you could look at how sparse they are, but it's not just
Yeah,
as
so
sparse, it's also
that's-
like, they are very carefully crafted.
Superposition and tunneling are.
For
Yes,
example,
sparseness, location.
Sparseness, location, and relationship, yeah.
Like,
And the proof basically comes down
I mean,
to
the tunneling is usually.
Because I have
usually you can't
certain
optimization.
that I want to work on, right? I give you a Boolean circuit,
Yeah, the optimization.
and I give you an output, and that input.
Teleportation is.
I didn't take on faith that that's a hard problem.
Oh, I
Things
see.
like
Because if
teleportation.
that wasn't
Yeah,
a hard
so you
problem,
have
the
Device,
system, you
teleporting gates
whatever.
even, like these
I can
operations,
give
like,
you Sudoku.
let's say
Oh, I see.
build
two
that
qubits on the opposite side of
such
a
that solving the
device talking to
Sudoku
each
is
other.
the same thing as
You don't really
undoing
have
this
this problem as much.
You'll need that one case.
And you need that one case, because then as a circuit gets bigger, I just build bigger and bigger
And so there are
Sudokus
ways
that match the size of the circuit
this
that
that
help you in the
doesn't
circuit.
just
Which also,
require you to like basically.
if there's a number you want to
swap
factor,
this qubit around.
I
with
can
something
hand you a
close.
Sudoku where by solving the Sudoku, to learn the bits of the prime
Basically,
factors
you
of
have to do some intermediate measurements on.
I'm not sure it'd be a good
the
Sudoku
operations
to
of
solve,
the qubits
but
that are
I think it's a fun
connected.
idea.
But
Right?
you can basically, you can basically do a smaller subset of operations and then measure a subset of qubits. And the effect is basically.
You're having to generally have, don't even.
That's
Sudoku like 50 times.
It's a good example.
People solve an idea, people have it solved, it's just, it's hard to do now. Some people have done.
I'm not privy to Kenka. I'm not.
Yeah. This is paper published on the IBM.
And with those who cannot go good.
How does that compare to
Yeah, so it's, the difference is that you need to be able to do measurements.
Yeah, 4x4.
Intermediate measurements, so you need to be able to, during the gate operation, you need to measure, assess the state of the qubit, and then
You
do
don't know
other
whether this goes
local
up.
operations.
So
So
yeah, you can measure where.
effectively what you do is you try to create an entanglement between those two qubits without actually
So that's what
swapping all the information around. You create an effective entanglement, so you measure subset qubits based on that outcome, decide what local operations and it gives you effective measurement. It's cheaper in the sense that you don't have to swap this. It's potentially costly if your measured operations are long or noisy in. Typically with qubits, those discussion operations. So your gate times are on the order of seconds.
No, it sounds, do you know?
Measured operations on the order of like.
Yeah, it sounds similar.
Like.
Of course,
And with decoherence times that are short, that can be a challenge.
That sounds like a stress.
I do not know.
I'm glad she's strong like that.
Yeah. That's probably a good question for. For the quantum.
What's the question?
The time scale of transporting an ion.
What was it called? Reconstructing string based on.
Ring reconstruction, substring composition.
I know it's fast. In other senses.
Although, quadratic is still derivative from the numbers game.
So
Right.
our quantum computer allows like.
Also, with there can exist quantum exponential speed ups of a problem
Modalities of quantum computing.
outside of the
Together, so.
right? They just have to lie in P space, which is
Right, so I mean.
the problem with those. So like that's what like the
That's what
quantum
happens when you
is
actually
like
have
exponential
this
speed ups.
environment for the
Like a lot of those problems, right? You don't have easily verifiable speed.
But
But then the problem is they don't have easily verifiable.
this is like,
So like, if you're using a quantum algorithm for material science, like it's come up that during this conference, when you check the answers, like as soon as it starts to surpass classical compute power, it's like, well, hopefully it's right.
You're gonna
know?
make grids of these things.
At least with something like factoring, if the quantum computer makes sense, multiply back and see if you get the number back and feel good about it. So that's.
Oh, I see.
Very unfortunate.
It crosses.
Yeah.
Right.
Well, that's another kind of problem. So.
Let's talk a little bit more about the dinosaur.
Should we? Okay, so.
And you need to bring.
So.
You have a whiteboard here, but
I definitely saw one earlier.
Yeah.
Like on it.
here you go.
Does it have in contact with that?
Yes.
Yeah.
So, I don't know general architecture. So basically,
Three, with a lot of internships.
He was.
basically what it is,
We traveled
is
pretty
it's a
early.
storage room,
Like staging.
but it has two racetracks. An event, so if you've ever used like a mass spectrometer, basically you get an ion as the anode, and you put it on this magnetic storage ring, so the store, yeah, I know. You put it in this magnetic storage ring and it goes around, and there's basically like magnetic switch, and it kicks into this.
Yeah, I mean, how would
this
that
region. And so, it's actually this region where this side, where they pulse the atoms. And it's on this side where we have like a laser that pulses them and you can read it out. The laser like comes out. It's
Think about 3
seconds. This node that comes out, that's the.
Like you told me at the there are like.
Yeah, I mean, the truth is they're all different. Really small. This is a microscopic object. So you can measure
Moving on to toilet.
Oh,
Is it
okay.
better than full truck like that?
Let's think of
measure some of the air correction guys put all sorts of.
Yeah, so the CNOT is, I mean, the point that's right back there is your hardware native gates.
But it's basically like a weird combination. It's like if you had a mass spectrometer, if you build a mass spectrometer and
Building a system which allows you to apply like this minimalist.
very similar, like the actual gates are basically analogous.
What you need is
Like that's like 16
operations.
But on a mass spectrometer,
Is like
a very refined spectrometer.
which is this.
And the fish, I mean,
Everything. Everything. All this work is still
like it's equivalent to something like some
yeah, that's you.
comparisons with
It's kind of
HPC is not.
Yeah, it's the way how you implement this.
And so we often get asked like when we're installing this thing, like, do you have
So
that's other than because it operates at the
realize
temperatures of freezing box.
So like.
That's cheap. Because that's additional.
And then in combination with all the gates, you can surmount this.
We're bringing it up. It's good. But
Yeah, I was gonna say, let's wrap things up. I know somebody has to leave. Just take a quick 5-minute wrap up before everyone really disperses. You mind if I? Here.
No problem.
Yeah, it shows like it's.
Are these Alex?
I was just gonna say, they have like.
3 years.
Fair game like that. Send me now.
All right, we just wanted to do, so I'm gonna put up the survey, really appreciate you to do it, while we're wrapping things up. So I wanted to get a quick sense of the people we're meeting in the room, let's have maybe one or two people from each of the sections. Sort of report a little bit on the discussions. Obviously, we make these topics on purpose because these are incredibly important and they're topics in alignment with quantum computing. Where there's already extensive activity and it would be great to stimulate in these areas. But in terms of particular applications that you're interested, that you find yourselves in now, I'd love to hear a little bit more about that. So could someone maybe from the physics group maybe talk about what the types of discussions were around that?
Yeah, I can do that. So we had discussed a few different things. So one was we had 3 folks in the group that were interested in computational fluid dynamics. It's some of the work that we've done there. and sort of, what has quantum computing done in that area, which is an active area of research. The other thing that we were discussing was potential applications to high energy physics, whether or not there were, this is actually more related to sort of data fitting. And so, not sort of I'd say, not the simulation necessarily of like a sort of HEP interaction or something like that, but rather sort of data analysis part of it. We also discussed machine learning and the potential related to graph, I guess it's graphical, or is that what it was? Yeah, so like basically transform the graph, and whether or not we could do anything there. I think that was it for the missing thing.
What about the medicine direction? How would you guys,
Well, whenever there's a database search problem, right? We can get programming speed up because of the lowest search algorithm. But the issue is, I've never had classical quantum. What we call it conversion, the reading out. So the most promising problems, but this is general, not just in biology, medicine. The problems that are NP intermediate, because those problems, the quantum computer can yield an exponential speed up. And factoring is the problem of that. Right? Factors, non-practical. I know we were discussing there are other problems like finding if two graphs are same, determining whether a graph is equal to another graph. There's also an intermediate problem. In that case, again, the quantum algorithm gives us exponential speed up over a classical algorithm. And then we were discussing, if any problem can map to that, then this is where most cases can be. Intermediate problem. I see. But then, quantum computer gives us the exponential speed up rather than just a reading speed.
from the math side, chemistry part, we were talking, obviously, we spoke about it yesterday, but DMFT was a good area for us, I think. To modeling systems at the atomic level, this was a good idea for hybrid classical quantum approaches. So we were all in that same sort of bubble. But I think this is great. Two additional comments. So Greg and I are very interested in stimulating more activity on campus. One of the things that we've been talking about is possibly acquiring some time from one of these hardware. Obviously, continuing would be great, but if we could acquire hardware time, right? We could do something like a call where we put out a call and we invite people to write proposals to use some of the time. And so we can start stimulating it in that direction. So I don't want to put anyone on the spot, but I think that this could be a really interesting opportunity to start stimulating challenges and something that I think we can do in the short term. How many of you already use Arch? Anyone here use Arch? So Arch is the computing cluster facilities at Hopkins. It's fantastic, right? The team there is wonderful. I've worked on a number of computers and the ones, I'm not just saying this because I know them very well, but the team is excellent, right? They're really responsive and a relatively small team, and they're very, very effective. I think something we can do in the short term to facilitate this is we can get one of these emulators on running that Arch, right? And so if you have obviously the challenge here would be figuring out what is the problem that you're thinking about and how does that map to one of these quantum computing algorithms or circuitry that we need. And so along the way about thinking about that, you can test it on the emulator, right? Effectively for free. It's not free, you need to use GPU time, but it's much cheaper than what you would on a regular hardware. So I think we're trying to put those pieces together for that. So keep that in the back of your mind that this could be something that could be coming to people here. So with that, I'll wrap it unless there's any questions. Listen, a day and a half of time when everyone has classes and research and everything is a lot to ask for. And we've been very excited with the participation, everything. So this was a really great to see so much engagement. So thank you for joining us. Thank you for the team, especially Quantinuum for coming to campus and giving these wonderful lectures. And with that, we conclude. So thank you very much.
And one thing I'll say, if you have any questions or you'd like to talk further, please feel free to contact us.
Yeah, oh yeah, right there, there you go.
And from Quantinuum, thank you for hosting this wonderful event. It's been great interacting with you and your students as well as APL. It's really awesome to see the uptake and interest in our systems, and please don't hesitate to reach out. I believe you know how to do so. So thank you.
Thank you.